Okay, well, maybe once I get started then, I'd like to welcome everyone back to our first hands-on session. And again, I really got to stress the idea with these sessions is for you guys to get some experience, doing some simple data analysis in Python and to ask questions. If you have problems, you don't understand something, please stop and interject either on Slack, or I'm sure Laura won't mind if you stop her and ask questions during her talk. So with that, I'll hand over to Laura now, and she's going to give you a small introduction to kind of Sunpi and I guess its various capabilities.
Yep, thanks, Jane. Let's see. Hopefully you guys can see this.
Yep.
Yeah. Okay. Hey everyone. So I'm Laura. I'm a postdoctoral researcher at DIAS as well. And yeah, I work in solar physics. So today's hands-on session is going to be really focused on kind of more an introductory session to Sunpi and kind of doing solar data analysis in Python. So I'm just going to give a quick kind of overview of Sunpi for people that aren't fully aware of it, and kind of some of the kind of key things we'll be doing today. And then the kind of tutorial that we have for today is kind of more of a show and a demonstration. Like I'll be doing a lot of talking just to kind of give you kind of what you need for the next sessions in the following days. But as Shane said, it is more of a workshop. Please jump in and ask questions if at any point something's not clear. I'm just going to do 10 minutes now to give an introduction to solar data analysis of Sunpi. And again, I keep doing this SSW. This space weather workshop is SWW, but I mean, a lot of you might have used IDL and will be aware of SSW within IDL. And this is why we keep making this typo. But if you are using IDL and you're using SSW for your solar data analysis, we're kind of at a position now with Sunpi and its growth that most of the stuff that is available within SSW, the functionality is available in Sunpi. So kind of hopefully this will make clear throughout this talk. So just kind of a introduction to people who haven't maybe used software for their analysis. They're really kind of beginning their research. Why as solar physicists do we need software? And the reason is essentially that we have so much data, all right, and we're doing kind of analysis on lots of different types of data. So when we study the sun, we can study things from solar events, what Shane talked about today, from solar flares to CMEs. We can study the sun as a star and treat it as a star similar to other stars and compare it in full disk observations. We have things like space weather, so we're trying to understand how these kind of solar events are going to impact the heliosphere and impact the near Earth environment. And then from a plasma physics perspective, it is a plasma lab in the sky. So in this sense, we have lots of different data sources that answer lots of different questions. And in terms of the measurements we look at, we have so many observations. This is a snapshot from the HSO, the Heliophysics System Observatory, which are.
Sorry to interrupt. We still see your front slide. Is that supposed to be the way?
Oh no, whoops. Let's see. Just bear with me here. It should be on this one now.
Yeah, I see here. That's the slide with satellites now. Yeah.
Maybe I'll just leave it like this, just to make sure it's working. Okay. Yeah. So this is thank them. So yeah. So this is kind of just a snapshot of the missions that are available, right now, and the data that's available, kind of in looking at the sun and then in the heliosphere and magnetosphere. And we have data from, also from a lot of ground-based observatories such as radio and LOFAR and things like that. And in terms of data products, we have images. We have lots of images of the sun. We have lots of time series. This is like flux as a function of time and things like that. We also have spectra. So for this reason, we kind of need software to be able to, get access to this data, download this data. These data come in lots of different sources, such as like FITS files, CDF files, text files, CSV files, name your file. I'm sure some spacecraft has some files associated with it. And then also we need a way to kind of deal with different coordinate systems. So, we have to be able to deal with an observation that's, say, from stereo and then also from a ground-based observatory. And how do you kind of work with the world coordinate systems to operate between those observations? And then once you have this data, you want to do some, manipulation and exploration and visualization with it. And this is where kind of like this, why you need a software environment and why you need a scientific workflow to do your analysis. So this kind of leads on to what is Sunpi. So I'm sure lots of you have heard about it before, but just this is kind of its description. So the Sunpi Project, so that's the project as a whole, facilitates and promotes the use and development of several community-led, free and open source data analysis software packages for solar physics based on the scientific Python environment. So Sunpi has a core package, which is Sunpi, But the Sunpi project is bigger than that. It's kind of where you can have affiliated packages. It's also to have a community-driven software development. So you can have, we'll see this week we have Radio Spectre, which is an affiliated Sunpi package, so it doesn't live within Sunpi core. And in terms of the project itself, it has kind of two main goals. It has a goal to have functionality to provide essentially scientific or Python tools to do your analysis. And I think what's key here is, it's giving you the tools to kind of get access into the ecosystem of Python itself. I mean, there's lots of different, software out there in terms of like machine learning, data visualization that, Sunpi doesn't need to recreate, but once you have your data within kind of this Pyco ecosystem, then you're kind of free to use whatever packages you like. The idea is not within Sunpi core to calibrate data. It's like, so you already come with your calibrated data and you then visualize it and do your manipulation. And the idea is then to not reinvent the wheel, to we leverage an awful lot of code that's kind of available within Astrophy, which we'll see today as well. And then support kind of, and this goes back to the Sunpi project, to support packages that are like niche. So you might have like a lofar.ie that would live within the Sunpi ecosystem and be supported by the Sunpi community, but it's not within Sunpi itself, because that's kind of more for individual researchers and things like that. And in terms of like a cultural thing, which I think is really nice, is try to build an open community that is open to everyone and inclusive to everyone. And again, anyone can contribute. It's open developed. So, you can see where the code is. If you have a bug, you can raise it and see where that fix is going. It's not like you need to know somebody essentially to get a bug report to get your code fixed. It's also an idea to kind of coordinate development. A lot of time as researchers, we write our own code for a specific topic, and lots of researchers write the same bit of code. So it's really to kind of coordinate development on that. And have kind of version controlled. And I think really key is like when you're doing science, you want to have reproducible science. So you want to have version controlled stuff so you can say, I did this analysis with Sunpi 2.0 and someone can recreate it.
If I could just put in there, Laura,
yeah.
I think for anyone who uses SSW, do you know how you would get new software into SSW? Do you know how you would fix a bug in something that you found in SSW other than fixing it locally on your machine? I think that's one of the main differences with Sunpi and that sort of idea, is that it's completely open development. You can go up, you can see the code, you can make issues, you can ask people questions. And so it really makes it a democracy. Like, it's not software that's controlled by some group of people at NASA or instrument teams. It really is open software to everyone. And I think that's one of the biggest differences. It's not really that it's IDL or Python. It's more this open development principle. Sorry.
Yeah, no, absolutely. Thanks, Shane, about that. And that's key. And something kind of sometimes hard to get your head around, but once you kind of get involved in this community, you kind of see that the way it kind of goes. In terms of just an overview of what Sunpi provides, it can kind of be divided into three main parts. And this is kind of the three main parts we'll talk about today. It provides kind of a way to get data, so data retrieval, and allows you to get data irrespective of kind of the underlying client or the source it's coming from. So, I mean, so people might be used to like the VSO, the Virtual Solar Observatory, which hosts an awful lot of solar data. Similarly, the JSOC, which provides all the AIA data and the HMI data. NOAA provides a load of data, and then any kind of data that's available on FTP or HTTP server. Sunpi has this nice way that you can search and download data through FIDO, which we talk a lot about today. So it kind of gives you this process to, if you don't really care where your data comes from, you just want your data. And a very kind of nice way to do this. So you're a little happy scientist here, you get your data. And once you get your data, you want to have different ways you contain it and read it in and manipulate it. So Sunpi provides data containers for this. So, you have a FITS file or any type of file that's holding your data. You can read it into these data containers, which hold both the data array. So you can think of like an image array or an NumPy array. And then it also has associated metadata. So this is, the units associated with that data, the coordinate system associated with that data. And at the moment, what's available in Sunpi is a thing of maps. So looking at kind of images of the sun and also time series. So again, looking at time series of the sun. So we'll talk about these two different types of data containers today. And then finally, I think one of the most powerful things that's really been developed over the past few years in Sunpi is the coordinate stack. And this builds heavily on the Astrophy coordinate stack. And it allows kind of, user-friendly ways to work with data from different coordinate systems. So this is just an example. Imagine you have one satellite at Earth and it's looking at the sun and there's a flare in the center of the sun. But you have another satellite over here and it's looking at the sun this angle, it'll see that same flare on the limb of the sun. So how do you deal with ways to coordinate those observations and kind of make scientifically ready data. And this is becoming more and more important with things like Solar Orbiter that Shane talked about, and also Parker Solar Probe, which are kind of really away from Earth and looking at the sun at very different viewing angles. And then also with this, again, just to highlight, it gives you a kind of a gateway into using the Python ecosystem. So once you've kind of read your data in, you have it in these data containers, you can manipulate the data arrays. So it doesn't have to be a NumPy array. You could use a Dask array. Then you can build on, to do like parallelization for large data streams. And you can also use the things like all the machine learning tools that are available in Python. So again, just going to highlight that. So just to kind of quickly go through those three main parts, and then we'll get on to the workshop. So the data retriever, this is called Fido. So it's a unified API essentially for searching and downloading data. So you have some data, it goes to some data source, whether that be at NASA, whether that be at like Lockheed Martin, whether it be at wherever.
Right. Sorry, Laura.
Yeah.
Should we work alongside you on this, or would you rather we waited until the end, or how?
Yeah, no, I'll quickly nearly finished, and then we'll go through all of this individually.
Okay.
Yeah. So just to kind of highlight, Fido, very easy way to do it. There's a snippet of code. We'll look at this in a moment. Then in terms of data containers, we have time series and map, which we'll also look at in the notebook. I'll talk a little bit more about this after. And then this is an important plot that I just want to highlight. Coordinate systems are complicated. And we are mainly used to looking at helioprojective Cartesian in solar, right? So that's you're looking at X, Y, and everything's in arc seconds. So what Sunpi does is it builds on these coordinate frames that are developed in Astropy and has ways to easily transform between each of them. The one thing I want to highlight here is that there are observer-based coordinate frames and ones that are not observer-based coordinate frames. And this becomes really important when you need to have a coordinate frame based, at Earth or at a spacecraft, and that will become apparent when we're looking at maps. So I definitely go and if you're recommending reading more about this, the Sunpi documentation. And as a snapshot of things you can do, you have two observations, say AIA and stereo. You define an active region in a loop in AIA. You can then take those coordinates and see where exactly that would be on stereo. And you can do this all within Sunpi in a very nice and straightforward way, which before is a very challenging thing to do. So finally, our documentation, there's lots of different, there's a user guide, there's lots of different examples in the example gallery. And at the kind of end of this tutorial and at the exercise session, I want you to kind of, once you've done the exercises, go to the example gallery and see what you can do with different kind of cool things with the data that you'll have loaded in. And then finally, just again, looking ahead, how do you get help? Again, Sunpi is this ecosystem. Sunpi builds on Astropy, and then lots of different affiliated packages build on Sunpi. So have that kind of thought process in your mind. So when we're thinking about using radio spectra, or Peter mentioned PFSS, so there's PFSS Pi, which builds on Sunpi, and all of these things you can do then within this ecosystem. And of course, today, when we're kind of going through our notebooks, you can of course ask us questions here. And there are no stupid questions. As simple as like you might be, please ask them. But when you go away from today and you kind of go on to do your research, how do you get help? Of course, you can come back and ask us, but it's better to get involved in the community. Go check out the GitHub, and you can raise issues and bugs and ask for feature requests. There's like an instant message or chat. There's somebody always online to help you with questions. So this is the link here. And then finally, we have this new Discourse Form. So this will kind of allow you to then, you can like show cool stuff you did. You can ask questions. It's kind of like a Stack Overflow for Sunpi. This is a new thing we've really recently set up. So yeah, so that was kind of just an introduction. So now we're going to get to the actual hands-on tutorial. But before we do that, does anybody have any questions? We're going to kind of go through and do a quick bug fix and see if anybody had issues with getting set up so far. Peter, you got sort of
a question, Laura, on the frames slide that you showed, and that tree that you showed, and you said there was a difference between observer frames and some other ones. So what were the other ones? So there's observer frames and there's something else.
Yeah, so I guess hopefully you can see this again.
Yeah.
So I mean, so heliographic Stonyhurst, it is a coordinate frame that's defined at Earth, right? So you can't have a heliographic Stonyhurst frame, really on Mars, right? It doesn't make sense. So if you're trying to think about ways, you have a coordinate in heliographic Stonyhurst, and you want to like move it to heliographic, like a helioprojective Cartesian coordinate, you have to tell it, what observer are you in the helioprojective coordinate frame, right? Because it doesn't know whether you want a helioprojective coordinate at Earth, or do you want it at Mars, or do you want it on your spacecraft.
Yeah,
I think this is where a lot of people get hung up.
The ones in the red box are Earth-based. Yeah.
Yeah.
And then the ones in the orange could be anywhere.
Yeah, exactly.
Yeah.
I mean, you can see by the word, and I guess these ones are really
sun-based, right? Or Earth-based.
Say again?
They could be sun-based or sun-centered or Earth-centered.
Yeah, so these ones are Earth-centered, I guess. But then, well, it's heliocentric is not, but you know, it's heliocentric in the sense that it's defined as the sun, the heliocentric. But these are then observer-based. And I guess this red box is just meaning that these are the ones within Sunpi generally used by solar physicists.
Okay.
So they've kind of just been built out of these ones. And you can add more, I mean, if you want, if there are any others.
Can I ask a question? Laura, are the spice functions part of Sunpi or somehow connected?
Not at the moment. There has been talks to kind of build upon kind of the availability of things like they're all the functionality is available within SpicyPy. I'm not sure if you're aware of that. So that's packaged, and I think there is some work to do with SpacePy. Have kind of methods to use spice kernels within them that they think they're trying to look at putting them into Sunpi. But currently at the moment, unless Shane, do you know if people are building on this at the moment?
No. Yeah, I mean, but essentially, a lot of the stuff you can do with the Sunpi coordinate stack. And, okay, the advanced functionalities of spice kernels you can't, but a lot of it should be compatible. But yeah, it's a work in progress. Spice kernels are hard to deal with, so.
But we have ways you can. So I'll show in one of the examples in the notebook that you can query JPL horizons, for example, and get coordinates of spacecraft. They might not be as accurate as the spice kernels, but they work.
I think they come from the same place, right? I think it's the same thing. They should.
Yeah, I guess sometimes they can be reading old ones, but most of it should be correct, right? In theory.
I think the positions that you get from JPL horizons should be fine. It's more if you're looking for the pointing of the spacecraft, that's a lot more complicated and can change with spacecraft off pointing. So I think the positions from JPL should be pretty good, but yeah, if you're looking for anything else, you need to go to the spice kernels for the appropriate mission.
Okay, are we ready to do some Python? Okay, is anybody having any major issues? Can everyone load a notebook? Maybe we should ask, can anyone not load a notebook? We'll spend a few minutes.
Yeah, maybe if you can't load a notebook, pop a message in the chat window or Slack window or something, just so we know and we can try and help. Because you'll really get the best out of this if you're able to follow along and change things. Like there's dates and times and other things, and if you can change them and break them, that's kind of good. I think.
Yeah, people seem to be shy, but they shouldn't be, really.
Yeah. Okay, maybe I'll just share my screen quickly just to show if people are too shy to ask. Can you see my screen?
Yeah.
Okay, so this is the GitHub repository where all of our notebooks are currently at the moment, right? So today we're going to look at this day one solar sources. So just to kind of, if you have not yet got this working and you cannot get it working, you can launch Binder. Let's see. And what this will do, this will spin up a notebook. It will just take a few minutes to spin up, but then you'll be able to access these through your web browser and run them. The problem is that when you go away from here today, you have to do this every time. You don't have it running locally, but this is a backup if anybody's stuck. But if you're not stuck and you manage to, the instructions where you wanted to fork this repository, and then you have it locally. So I'm currently in this. You
might want to increase your font size a bit, Laura. I don't think.
Go, yeah.
Sorry.
Just do that in. Okay, is that okay?
I think so, yeah.
Yeah. I'll be going to the notebook in a second, but this is just to show what. Okay, so I'm currently in this. I've cloned it. So if I git remote -v, you can see I've cloned it. So the upstream one is the notebooks, and I have it locally, or I have it on my own local GitHub as well. So the main thing you wanted to do is you wanted to create a conv environment from this environment file. So the instructions were on the website. So we want to kind of go to that environment. So if you want to kind of list your environment, you can go conda info -e, and it will show you the different conda environments you currently have. So I've already created this stellar-sww environment, and I'm currently in my base one. So I want to get there. So I can go conda activate stellar-sww. And now you can see I'm in this stellar-sww environment. So in that environment, what that means is that within that environment YAML file, it has all the kind of modules that we're going to use, or those Python packages, and it will set them up for you already. So these are the ones that we're using. So in your base, it might already work if you have Sunpi installed, but to make sure that it's going to work within this environment, use the environment YAML file. So now that we have that, we can do Jupyter Notebook, and what that's going to do is going to start a Jupyter Notebook within this environment. Now, one thing to say, if you download the environment file, you know, this morning or last night, it won't have Jupyter installed. So what you'll need to do is do conda install a Jupyter, Jupyter hub. So if you're still having issues, please put in the chat, and one of us will help you. As you can see, this is opening a thing. But it should open it to your default browser, or you can copy and paste, and you can run it in your local host here, which I'm going to do. So we're going to go day one, and we're going to go solar sources. Okay. And this should start getting set up. Has anybody managed to do this, or is anybody having any issues so far?
I managed to open mine, at least, which is good news.
Yeah.
Yeah. Maybe if people could give even thumbs up.
Yeah.
Mohammed opened it.
Cool.
Yeah. Looks
And
good
like,
from people. Yeah.
Yeah. And if you're so lost that you don't even know what to ask, that's also okay. Please write in the Slack channel, be like, I don't even know where to begin, and we'll help you get in there. Because sometimes this can be hard when you're not used to, if you're new to Python or anything like that. That's totally okay.
There's lots of terms and terminology and words and stuff that you may not have a clue about. So like definitely just ask.
Yeah.
We've all
it's okay to be confused. Oh, sorry. Yeah.
We've all been there where we know nothing, and it's just really confusing.
Yeah. Okay, so the way this notebook is going to run, it's going to be a lot of me talking. So please butt in and ask questions, whether it be like literally anything, or somebody stop me or clarify things. So as again, I kind of gave an introduction to Sunpi, and in this notebook, we're going to go through all the kind of things that I talked about, all the main functionality that's within Sunpi. And at the end of this notebook, building on everything that I've shown, we're going to go away and look at events. So I'm going to give you a date. You're going to go and do your own analysis. So hopefully then you'll be able to build on it. So kind of when you're going through, make sure you ask questions, because at the end, or of course you can ask questions at the end. But we kind of want you to be able to go away from this and actually do your own analysis. So the notebook is divided into several sections. I'm going to talk about introduction to Astrophy Units. So as I said before, Sunpi is really heavily built upon Astrophy, which is a Python package for astrophysics. So it's quite general. It has an awful lot of functionality there. So I'm going to give an introduction to units, because they're used throughout Sunpi. Then I'm going to give a very brief introduction to how coordinates are used in Sunpi, because we'll need that to then look at how we work with maps. I'm going to go through how you can then search and download data from different instruments and different wavelengths. We'll look at the two data containers, map and time series. We'll then look at how you plot and manipulate the data, and then we'll do that exercise, as I said. So to begin, what we're going to do is we're going to import all the packages and sub-packages that we're going to use in this notebook. So just to kind of give a little description, so these ones are all the Sunpi-based packages. So in sunpi.net, we're going to import Fido. So I already kind of touched on Fido. This is our unified API. And attributes, which is our attributes. So we're going to import attributes as A. So anytime we call A, it's going to call this sunpi.net.attributes. And similarly, in the coordinates package, we're going to import several different functions. We're going to import Sunpi time series, Sunpi map, and I'll talk a little bit more about this in the line. Then two of the Astrophy functionalities that we'll be using, and then the general matplotlib and numpy. And of course, you could import these at any point in the notebook, but we're just going to import them all at the top for ease. So to begin, Astrophy Units. So what are Astrophy Units? It is kind of this functionality that kind of gives you the ability to deal with units in Python and within this way. So it has kind of a way, so you have any numbers or any arrays, you can then have an associated physical unit or associated physical quantity associated with that. And that's important when you're doing things like manipulation of data, you're multiplying data, and it also is a good way to kind of keep making sure all your calculations are in check. Does it make sense to multiply those two arrays together if they're in different units or in different non-compatible units and things like that? And why it's important is that we have within Sunpi, any physical input or output is given as an Astropy quantity. So for example, if you're searching for a wavelength range, you have to give it in like an angstrom or in nanometers and things like that. So how we create units, so we've imported Astropy units as U. So let's create just a value, say distance in kilometers, which is 10 kilometers. So to do this, we say just like add, it can be an int, it can be an array, it can be a float. And we say by u.kilometers. And then when we print distance in kilometers, we can see it has its associated unit. Now with Astropy units, it has a value, so this goes back to the actual number that we gave it. And it also has a unit. What's really powerful is then you can then transform between different unit systems. So we want to say, for example, this distance in CGS units, you can say .cgs and it will tell you what that unit is. And this is really important then if you're kind of multiplying, say, between SI units and CGS units, this will take care of all of that without you having to worry, or maybe even a sanity check. You can then convert between units. So let's convert this kilometers to megameters. You can see it's 0.01 megameters. You can convert it to parsecs. But again, as kind of like to make sure you're not gone mad, you can try convert it to seconds, and you can see you're going to raise an error because you can't convert a kilometer to a second. So you'll probably come across this a lot where you've done something a little bit wrong, and it will usually give you a unit conversion error. So just something to keep in mind. And then let's say, for example, you can multiply things, you can add things. So let's just create a second. So we say 60 seconds. And then if you divide the distance in kilometer by time in seconds, you can see it's carried over the unit, right? So now you have essentially a velocity associated with that. So that's just a very, very quick introduction. But if you want to kind of see what the units are, you can go U tab, and it should show you all the different units that you can write down. So that's just like the U tab. So as you maybe can imagine, this is kind of a powerful way to do science, right? You want to make sure you have units associated with your data, and just something to keep in mind when we go through this notebook, that they'll pop up again and again and again. Does anybody have any questions so far? Or any comments?
I have a quick one, Laura.
Yeah.
So it's Pierce here.
Hey, Pierce.
What does this only work with Astropy, or does it like interact with NumPy as well and Matplotlib? Or because I found myself sometimes basically having to just force it to be the dot value for different things. Is there like a handy way of knowing what it works with, if that makes sense?
Yeah, that's a good question. I mean, you can have a NumPy array it has an associated unit, but yeah, if you're plotting it, for example, it will see that it's not a NumPy array, so you will have to do dot values. So I guess it really depends. As packages that usually would depend on Astropy would be okay with it, but those that aren't are probably not okay with it.
I think as well that it's improved an awful lot. So now a lot of NumPy stuff will work with an Astropy quantity. So I'd say the vast majority of things you can do to a normal NumPy array, you can do to a quantity. And then for the plotting stuff that Laura mentioned, Astropy has this thing called quantity support and time support, which means that Matplotlib can understand them and plot them properly for you as well. So you can make Matplotlib basically understand quantities.
Yeah, and we'll see that a little bit when we start to plot maps. But if you just use Matplotlib out of the box, sometimes there can be something. But yeah, as you said, Jane, it's definitely coming along. But Pierce, again, if you find a problem like that, raise an issue and be like, why is this annoying? This is annoying me. Is there a way around it?
I guess is there any limit to the complexity of those units? Can you have like a huge expression or some unit like specific intensity has what, like 5 units in it, and then like there's no limit, I guess. It can handle it easily.
Yeah, the problem, it does slow things down. And this is something that you have to kind of be aware. If you're doing large calculations, you might want to, get your 2 arrays into the same units, take them out of the Astropy units and put them back in at the end. But just something to keep in mind when you're doing large calculations. Those unit conversions can take some time.
Yeah. Okay.
Yeah. Is that okay? Anybody have any other questions? Okay, so I guess building.
Actually, I have a quick question. Hi,
Yeah.
Laura. It's
Hey.
Elena. Are we supposed to be seeing the same thing as you in the Jupyter Notebook? Because I am actually not seeing that.
You're not. What are you not seeing? Any of you?
I am seeing a very, very short from Sunpi.net import, whatever, but it's like 3 or 4 lines, and that's it.
That's the other file.
Oh yeah, so I think you want to go to the solar sources.
Yeah, I see only example day 1. That's it.
Oh, okay. So what you need to do is you're going to have to git pull upstream mass main, because I think it's updated. You must have done it the other day before the notebook.
Yeah, I did it a couple of days ago.
Yeah, so it should be there now.
Okay,
so-
okay, I'll do that now. Thanks.
Yeah, thanks for raising that.
Maybe, Laura, can you just do it yourself, or just write the command yourself, just
Yeah.
in case other people have that same issue?
Yeah, so you do git pull. Well, I guess it hopefully
That
it'll
was
be pulled
origin
here.
main, wasn't it?
Say again?
I think it'd be origin main for
Okay.
them. They won't have it.
Yeah.
I think that's the default.
Yeah, if you don't know what it's called, you can do git remote -v, and you can see here, I have called mine upstream, but yours might be called origin. So whatever it's called here, you go git pull that, and it should work then. And what that will do is just pull those notebooks into your local repository, so then they should be there.
Just to say as well, Laura, when I did mine, upstream wasn't there, and I had to add it in. So just so
Yeah, so you can add, if you want to add, so this remote might have called mine origin, which is my Hazlo one. So you can just rename with them whatever you want.
Yeah, but by default, it'll just be origin and should point to whatever you get cloned it from. I wouldn't worry about the upstream thing. That's
Yeah.
I think that Janina, if you get that working, just shout and let us know, just to make sure it works. I guess we can continue.
Yeah. Okay, so building on units, we'll now talk about coordinates. And similar to units, Sunpi really uses Astropy coordinates throughout the whole of Sunpi, and essentially is a way to represent points in physical space. And this again, it's allowing you to do like in 3D space or into projected coordinates on an image. So this is important for like helioprojective coordinates or anything we're looking at, a picture on the sun, a point projected onto the sun. And what's different in Sunpi coordinates and Astropy coordinates is that it builds upon Astropy coordinates, it builds on top of that. And again, it allows you to kind of use solar physics coordinate systems. So that was that plot that I showed you before of how all those different coordinate systems work together. It then also kind of gives you ways to get locations of solar system bodies. So kind of this goes back to kind of using ephemeris and using JPL horizons to get solar system bodies and get them in kind of coordinate frames that are used in solar physics. And different kind of ways to calculate sun-specific coordinate information that is used within solar physics. So kind of the one main thing that is really kind of hard sometimes to get your head around, but when you do it, it does make a good bit of sense. So we deal with coordinates to write this whole notebook and to write Sunpi is using this sky coordinate class. So a sky coordinate object is an Astropy object which combines positional data with a coordinate frame. So similar to kind of a unit where you have a value in a unit, a sky coord is a positional data and a coordinate frame. So whether that be helioprojective, whether it be ICRS, whatever coordinate frame you're working in. And this is where, again, these frames come into. In Sunpi, we have these solar specific coordinate frames that we can define a point around. So let's look at how we kind of create a sky coordinate object. So what we're going to do is we're just going to name it HES coord. So we're going to make a heliographic Stonyhurst coordinate. This is our object, and we're going to pass it a latitude and a longitude, an observing time, and then the frame. So this is kind of how you create a sky coordinate object. So you can think of latitude, longitude. This is the position on the sun, an observing time, and a frame. And if we run that, we can see now we've created a sky coordinate object, and it gives you all the information associated with it. Let's just print out the different things associated. So we can go the latitude and longitude to get those values. We can look at the radius, which is 1 because it's the radius of the sun. And we can also convert it to things like, this is in latitude and longitude. That's we wanted in Cartesian coordinates. You can get an X, Y, and Z value. So it's kind of a nice way then you can play around with. So dot X, dot Y, you can pull out those different values. the power lies in being able to transform this point into a different coordinate system. So say, for example, I want to get that point on the sun defined within heliographic solar years. What does that look like in a helioprojective frame from Earth? So what you can do is you can take that coordinate point, you can use this function transform to, and what you do is you pass in here a frame, different coordinate frame. So let's pass in the helioprojective coordinate frame with the observer base at Earth. We can run that. We can now have our values. If we look at here, let's call this HPC chord. And we can go HPC chord.tx. And we can see that then it's in arc seconds. So it's in 154 arc seconds. So that's a point on the sun then. And we can also print TY. So again, just to kind of go back to the idea, you create a sky coordinate object by giving it its inputs. So latitude, longitude, time. But for example, if you're creating a helioprojective one, you would give it in arc seconds because that's what's given for helioprojective frame. And then you can transform between them. You can also transform these chords into frames outside of Sunpi. You can transport them to the ICRS frame, for example, and get your value then in Orion deck. And this is kind of important if you're doing radio observations. A lot of the time your observations are in Orion deck, which you observe at a specific time. And then you can use this essentially stack to then build up your image and get it into a helioprojective frame to then compare with AIA or something like that. So that's a very quick introduction, but it's important because it will become clear later on why we need to use this. It's hard to kind of recognize the power or the usefulness of this right now. Does anybody have any questions so far? No, again, feel free to go talk in the chat.
Sorry, Laura, to cut across again. When it says observer equals Earth, is that like the center of Earth or where? Yeah.
yeah, this is a really good question, Pierce. So I think that is just, the center of Earth, right? And this is important because I actually had this problem the other day where, that's a good assumption a lot of the time because the sun's very far away. But if you're looking at the moon, for example, and an eclipse, right? If you have defined your point to be the center of the sun, but say, for example, you took observations with LOFAR in Ireland, Ireland saw the eclipse, but the center of the Earth didn't see the eclipse. So the moon is going to be completely off. So this has to be really careful about how specific you want your observer coordinate to be. It's usually fine for looking at the sun, but anything closer, you have to be very careful. Does that make sense?
Yeah. And then presumably you're able to define a point on Earth then for when you want to do close things, or
exactly, yeah. So you can define in Astropy there's a function called Earth location. Yeah, and you can then give it. You can actually even usually give it
a name. You can give it a name and a time, and it'll like try and resolve it.
Coordinates for is it Earth? Earth location. Okay. I think you can just try Dublin. Let's see. Oh. Something like this you can do.
Yeah.
Didn't like code. This is that bad. Anyway, yeah, you can pass Good. Anyway, yeah, you can find coordinate systems like that. So I think it's called Earth location. But that's a great question, Pierce. But yes, you can do that. But usually FITS files that have, if they're properly written FITS files will have the observer location in them. So you don't have to worry about that usually.
Laura, what if I don't believe the outputs? How do I, like, one thing that I would always do when I was using particular routines in SolarSoft was look at who wrote it. And then if there was a paper reference, I'd go and have a look at that as well. So why would I trust any of this?
Yeah, that's a good question. I mean, a lot of the time, compared to say SolarSoft is where someone just uploads a file, all code here is like, reviewed by, usually has to be 2 other developers to make sure that it's correct, and people can raise issues if they don't believe it. So I guess if you don't believe it, you can also raise an issue, say this is wrong. But there's usually, like with codes, especially with functions that are based on some scientific paper. There's usually a reference to that paper within the doc string.
Okay. So that's, I think that's what I wanted, is like, I'd like to see what the doc string is. So
Yeah.
how do I access that doc string?
So like, I mean, you can if you do question mark, like for example, again going Earth location, it'll tell you, this will tell you all of the notes.
Yeah.
On the docs. I mean, here maybe they don't have any things, but you can also go to the documentation on the website. We usually tell you.
Yeah.
But this will usually be how you access it.
I think as well, to add to that, like specifically for the coordinate stuff, in the test suite, we compare, Sunpi compares the values that it gets to reference almanac values. So that's another way that you can build up some trust, because you're absolutely right. You should never trust software, even Sunpi, off the bat. You should always convince yourself that it's doing the right thing. And like you say, you can compare the outputs from Sunpi to known values that you get from some other piece of software, but also the Sunpi tests itself, especially the coordinate stack, do compare to reference implementations in other languages and stuff like that.
Yeah, there's always a bug somewhere.
Yeah.
No matter how good it's been written and tested.
And also, a lot of the coordinates stack was revamped or rewritten by Albert Shi, and I think if he does it, you probably can trust it pretty well.
Yeah.
Yeah.
I think he actually found out that solar orbiters ephemeris was wrong.
That's right. Yeah.
You know, like, you know, he's a bit of a wizard, but this is the whole point of having a community-driven development. You know, if nobody uses this or nobody reports bugs, then it's never going to get fixed. So we want people to break it, essentially. We're asked those questions for sure. So okay, so just a final note on coordinate systems and coordinate frames. Again, to highlight the importance of having an observer for helioprojective, and that'll be the one that will come up again and again, is helioprojective. And I'm sure many of you who've used Sunpi to do coordinate stuff or maps have come across the problem where you try to transform a point and it says observer location is not given. So let's just create a helioprojective coordinate at Earth. So again, we're creating a point at the center of the sun, 0 arcseconds by 0 arcseconds. The observer is Earth. We're going to give it this obs time and say it's a helioprojective frame. We can print out that center, but say we want to see what that point looks like at, what is that coordinate in helioprojective at Mars? You can take that helioprojective coordinate point defined at Earth. You can then transform it to observer is Mars, and then you print that out. So you can see that the center of the sun, as viewed from Earth, if we look at that point on Mars, it's going to be at this location. So 500 arcseconds, and then, so you can see it's offset from the center. So this is important, again, if you're thinking about, you know, a point that you observe from SDO and you're comparing it with a point you observe from solar orbiter. And you can then nicely, with like this very simple one line of code, convert those points between each other, which is nice. So again, just to highlight, you need an observer when you're dealing with helioprojective frames. Okay, so that was kind of an introduction to what you need when we kind of go and looking at maps some more. But what I'm going to talk about now is how we can search and download data using Sunpi. So again, I've alluded to this Fido, which is Sunpi's Fido client for searching and downloading data, and it really is a unified downloader. And the idea behind Fido is to kind of give a single user interface that you can search and get data irrespective of the underlying client. So you can just do .search, you give it its parameters, and it will go away and search your data, regardless of whether it comes from the VSO or from JSOC or from some FTP server. And it gives you a way to kind of access multiple instruments, provide all data available within one query. It also allows you kind of to search for several different instruments at the same time and see what's available. Say, for example, you're doing some analysis on a solar flare and you have those times, you want to see what data is available, or you want to look for 2 specific observations from 2 different instruments and you want to do them in one search, and that's something you can do. And I think the key is, and this would be interesting for people more that are developing code or thinking of this in the future, is that it is extendable. So you can take Fido outside of Sunpi and you can build it then into your own package. So this is what Shane has done for radio spectra, which you'll see on, I think it's tomorrow, the next day, for dealing with radio data. So you can then, if you have some data that's served on a HTTP server, for example, you can write a Fido client that can go and get it and work in the same way. So currently what's available through Sunpi Core The data available is from the Virtual Solar Observatory, for those of you who know it. If not, go and look it up some more. The JSOC, this is again AIA and HMI data. A lot of individual data providers that people have written clients for. We also have the Helio event knowledge base, so you can query the HEK to see, look for flares or for active regions or for CMEs or things like that. We can also query Helio, which is another database that has a lot of different flare lists and things like that. So to begin, let's just look at FIDO. So above, if we go back to the top, we can see we've imported FIDO from sunpi.net. And we access data, we access different data sources through different clients that are within FIDO. But if we just print FIDO here, we can see all the different clients that are currently available within FIDO. So we can see there's an Eve client, which provides data from like the Eve instrument that's on board SDO, the GBM client that provides access to data from Fermi, GBM. We have all the different clients. We have the VSO client, which is the Virtual Solar Observatory, et cetera, et cetera. So to search these clients, we need to kind of build up a search query. And how is that done? And it uses attributes or attrs to search for data. And each different client is going to have a different set of attrs associated with it, depending on the instrument that you're looking for. So they're these parameters are used to kind of construct queries to look for, over a certain time period for a certain instrument and for a certain wavelength. And of course, these are the main three attributes that you'd be searching for. So let's look at how these can work in a little bit more detail. So we've imported above attrs as A. So A.time is then the attribute time and instrument wavelength and so on and so forth. So to build up, say, a time range query, you'd say A.time and you pass it a start time and an end time. And you can see then it's this object, which is a attribute giving a start time and an end time. Now, of course, if you try to give it an end time that's before the start time, it will say the end time must be after the start time. And then similarly, we have a lot of different instruments associated with the attrs that you can build upon. If you want to see what instruments are currently available, you can say a.instrument and just print it, and it will show you all the different instruments you can currently search FIDO for. And it will tell you also what client it comes from. So AIA comes from the VSO. If we go down a little bit further, you can see GBM comes from the GBM clients, et cetera, et cetera. So just in case you weren't aware of what you could get with FIDO, this is a good way to kind of have a little look. We also have tab autocomplete. So if you go a.instrument and go dot and click tab, it should come up with all the list of names that are currently available, which is important. So say, for example, you want EIT, you can do it like this as well. And it will know then you're searching for the Extreme Ultraviolet Imaging Telescope, etc. Now, if you want to look for a certain wavelength, for example, or a certain type of observation, again, as I said, we have a thing of Sunpi that any input or output that is associated with physical quantity has to be a unit. So if we want to search for a wavelength, we can't just give it a number, you have to give it a unit. So say, for example, we want 171 angstrom, it will be an angstrom. You can also give it in nanometers, for example, and it will know to look for, oops, nanometers. And we convert that to angstrom because that's just the default that is currently used. Now, so they're just an introduction to the attributes, but then how do you use them within FIDO to search for data? And this is how you construct a simple query. You say FIDO, you go .search, so this is a function in FIDO, and then you pass your attributes to it. So we're going to pass a time range, so a.time, and we can pass the instruments. So say we want, over this time, we look for all the data that's available from AIA. If we run that and then we print it out, this is going away, it's looking at the VSO, it's seeing what data is available within these kind of parameters. And you can see we have a result which returns to us a table of over 800 results, because AIA has, it has observations at many different wavelengths of 12-second cadence of each wavelength. So lots of different data. And it tells you kind of all the different information about each of these files. So each row is essentially one file. So it'll tell you, the source, the instrument, the wavelength, where you're getting it from, the type of, the size of the array. So these are 4K by 4K images. And then it also tells you other information like the exposure time and things like that.
Laura, can I ask you a question very briefly? There are many different time formats. Is there a way to find out what a.time takes?
That's a good question. Is there a way to do that?
You know,
I don't know off the top of my head, but I guess this one generally, I think you can also do it. It's fairly flexible in what way you can give it.
Hmm.
Yeah, probably if you try different things, it will read different things.
Yeah, it's pretty good. You know, if you really wanted to do this, you could pass an Astropy time object, and that would probably be your best bet to make sure you've done that correctly for parse time. So I would recommend just reading the documentation on that. But it's fairly flexible, and it will try search for most of the time formats that are available.
I guess it'd be interesting to see the difference between an American time and European time. So you put the month or the date in whatever position.
Yes,
so it's interesting to check for that if you have.
Very good point. Yeah, so it will always look in UTC.
Yeah,
Sorry.
but I mean, much more than that, you know, people use Julian date, modified Julian dates, day of year, and all those different types of time. So, you know, when you script something, when you write software using this type of thing.
That brings up a very good point. And what you can do is you can actually create a, maybe I'll show an example. So parse time is a function in Sunpi, which allows you to build kind of a time object within Sunpi. And you can give it lots of different things. So you can give it a date. If we have a look below. It's a time object, but I think you can just do.
Yeah, you should be able to just do.
You'll be able to convert between these different things, and you can also do things like if you want to give it, you know, oh, this is going to really wrong. You can also give it U time, and it will. Oops. Like that doesn't make sense because it's wrong, but you can give it lots of different time objects, and it will then convert between them, and you can pass them into time rather than being strings. So there's lots of different ways you can manipulate time within Sunpi. I just didn't allude to it here, but that's a really good point. That what you should do is if you have your data in modified Julian date or whatever you might have it in, you can first create a time object and then pass it in. And then you'll make sure that you're not going to have any problems. Is that okay?
Yeah. How do you do this auto completion to see the different functions inside or?
Oh yeah, so if you click dot and then you click tab, it should.
Tab?
Yes.
Doesn't work for me for some reason.
I think if you have a little bit of patience with the tab, if you type time_ample example dot and then hit tab, it takes a couple of seconds.
Okay.
Yeah. So,
No.
so this shows you all the different types of data climbs it can play around with. But definitely a good point. And we can talk about that a little bit later as well if you want to have more questions about time specific things. Okay, so just moving a little bit on. So we built a very simple query here. But say, for example, you know, this is returning all these different wavelengths. I know I only want to look at 171 angstrom. Let's specify our search a little bit further, and we can add in a wavelength. So we're going to add in, we only want AA data at 171 angstrom between these times, and we can run this again. And we can see it's returning a result, another table, but you can see now there's only 100 results, which is great. That's fantastic. But you know what? I don't need all of this data. I only want to look at data at a 2-second cadence. We can then further, you know, specify this query and add in an a.sample. So this is the sample time of your observations, and I only want the data every 2 minutes. And if we print this out, then we can see then we have around 10 results. That's grand. That's what I want. So this is kind of a way how you build and construct a query, and you can add in different attributes and specify it down even further to build your query. Now, something to note, we haven't downloaded any data yet. All we've done is search data and gotten return of the data that's available. So I've decided, okay, I like the results of this query. I want to download it. And how this is done is using fido.fetch. So you do fido.search to look for your data, fido.fetch to get your data down. And what you do to use fido.fetch, you pass in your result into the fetch. So this table is called the unified response table. It's a unified response object, and we're going to pass it into fido.fetch. So if we run this, we can see it's going to start to download those 10 files. Richard, come on, internet. And And what this has done is, we haven't told it where to download this data. So what it's doing is it's downloading it into a folder that's set up in your Sunpi config file, which should be Sunpi data. You can, of course, change this within your config file. So if we go print files, so it's returned the file path of where that's downloaded to, we can see it's downloaded it into this config file, Sunpi data, and then the name of the fits file. But say, for example, I said, I don't want them in there. I want them in a specific folder that I want to do my analysis in. I've created a folder called SWW tutorial. And what you could do is you can actually, download, you can do the same function here, fido.fetch, but then give it a path you want to define it to download that data to. So of course, if you download this notebook, you need to change that path to whatever you want to. You can also do, like, if you want it in your current working directory, you could just do // and that will download it into your current working directory. And what I'm doing here is I'm only downloading the first file because I don't want to download them all again. So what we've gone through is
sorry, will that, like, if you give that a folder that doesn't exist, will that create one for you, or?
I don't think so.
Yeah, I mean, I could easily just try it, I suppose, and see what happens.
Let's see what happens. Oh, it does create one. Okay, yeah, there you go. You can make up whatever file you want. You can also do things like, if you do something like this, it should create a file based on whatever instrument it is, which is kind of neat. Let's see if that works. Come on. So you can pass in different smart things here to create repositories to do things. Okay, it's having a mirror. But that's a good question, Bruce. So what we've seen so far is fido.search and fido.fetch, right? Very simply, how do you look for AI data? But say you want to make more complex queries, you want to look for different instruments, different wavelengths, different things like that. You can create more. I'm just going to interrupt that. You can create more complex queries by using the pipe operator. So this is, you're looking for this or this. And you can also use the AND operator for you want like this and this. So this is a way you can create more complex queries. So what we're going to do is we're going to look for results over this time range. And we're going to look for both GOES XRS data. So this is looking for X-ray data from the GOES instrument. And we're also going to look for AIA data at 171 angstrom. So if we run this, it's going to go away. It's going to look at two different clients to look for this data. And when we print the results, it should be 2. Don't know why it's taking a little bit of time.
The live demo gods are unhappy.
Yeah.
Do you know how often the data are updated? That is, what's the latest date for which I can download AA data, for example?
I guess that really depends on what the instrument providers give, right? You can get AIA near real-time data, I think, within an hour.
Right, but that's the low resolution, right?
Yeah. I think the full resolution is, I think, must be a day or two. Shane, do you know?
Yeah, I think it's a couple of days later, as far as I know.
Wow.
Yeah. Yeah, but you can search, for example, you could search for, like, give me the latest data, and it will only return the data that is available. But it will return near real-time data, so just something to be aware of. And the XRS data takes a few days as well, which is kind of annoying. But yeah, okay, so we've made this more complex query. We've looked for X-ray data and AAA data, and we can now see our result is actually linked too. So we have results from 2 providers, from the XRS client and from the VSO. So if we want to kind of index these tables, the first table is going to be the XRS data, and the second table is then going to be your VSO data. You can also, you want to kind of look at the table and query down some more. You can look at all the different column names and treat it like a table, which is kind of an interesting way if you want to then further specify your search. So let's just first download this XRS data, which we'll use below in our data containers. So this is looking at the first result and then the first row. So this is just downloading this one here. And I'm just going to download it locally. So you can pass whatever path you want to do here. And let's, for example, say I want to this is just an example to say, you know what, I don't want to have a look at all of these and I don't want to build even more complex query. I just want the time closest to, say, at this time here within this query. So we can find out what index of the table that's in, and then we can fetch, again, just the result of that query. So just to kind of give you an example of what I mean here. I only want this row, which satisfies the condition of this time. And I mean, you can search on basically any of those column names of things you might like, but I only want to say this file. And the reason I want this file is because we want to have a look at it below. And again, we're going to download it into our local path.
I think as well, you might, if you could just show the output without the argument, just to show that like it understands that that's like a time, a time difference. So like units and times are kind of all handled properly by like Sunpi and Astrophy. So you can take a difference between two times and it like does the right thing, and it'll even make sure that you convert, if the times are specified in different formats, it'll convert them into a common format for you if it can. So I think that addresses part of your questions, Carmen, that like if you've got times defined in different formats, if it can convert them, it will, and it'll do the subtractions and stuff for you.
Mm-hmm. Yeah. Okay, so that's kind of the end of kind of an introduction to how Fido.search and Fido.fetch works. In theory, it should work the exact same for whatever instrument you're looking for. Obviously, some instruments have their own instrument-specific clients. So for example, with the GOES client, you can search for a certain GOES in satellite number. So you can go a.goes.satellite number of 10 or 15 or whatever number you want. And this is why it's kind of hard to kind of document all of those attributes, because it's very instrument specific. So the best way is to kind of have a play around with it, look at our documentation. But in theory, it should be kind of similar to what I showed so far. Does anybody have any questions about that or comments?
Yeah, just to make sure, these are all remote observations, right? That can be accessed with Fido, right? Not in situ.
Well, I mean, in theory, you could have anything. I think you can get in situ observations with Fido at the moment. Sunpi really doesn't support too many data containers that look at in situ data, but you can get the data this way, for sure.
Okay. Yeah, I'm just looking at the list of instruments here. Yeah. Oh, there is Ernie. Okay, there's some.
It's primarily remote sensing data, but there's another package called HelioPy, which is kind of another sub-package, and that deals with a lot of in situ observations. And I think that has a Fido client as well, so you can do similar searches. At least I think it is.
Yeah, it does. It does.
And so, then, okay, cool. And then for some of the instruments, I see two sources.
Yeah.
So does it choose itself what where to load from?
So the idea behind Fido is it is going to return to you any available data, right? So this is where the user needs to decide where they want to get their data from. And I think this is a lot of questions we've actually had in Sunpi recently, is like, why do you have two different clients? And some example is, for example, the VSO doesn't provide level 1B data for SUVI, right? But it provides level 2 data. So if you do a search for SUVI data, it's going to return a SUVI client that we have that returns level 1.5 data, and then it's going to return the VSO data, which has the level 2 data. So I guess it's just to be kind of aware of what you want, and be aware that it's returning all available data. So always look at your result before you fetch the data.
And how do we select which source? Or is it just based on the indexing of the results?
Yeah, I'm trying to think of, let's just, let me think of them, yeah. Actually, this is a good one, I think. So I know that RESI, so for example, the VSO provides some RESI data, but it doesn't provide, say, the observing summary data. So we wrote our own client that also returns the observing summary data. So when we look at this result, all we've done is we've given it time in RESI, and we say, okay, these are two, it's now providing two data sources. And I say, oh, do you know what? I actually only want the one from the RESI client. You can then index, and it will then only return, this is the RESI client one. And then you can just download that one. Or similarly, if you want the other one, you can do one. You can also index it by name. You can also do this.
But presumably you should be able to choose the source at the search, so you don't spend that extra time searching for everything.
No, that's a really good point. It's something that we've actually been talking about recently. I don't think you can do it at the moment.
Okay.
But there's talks about putting that in. So you can say, you know what, only give me VSO data. This is where it's great to have user feedback, right? Because you can say, you know, I want to have a way to do that. Okay. Okay, so moving on, what we're going to do is, based on this GOES data and based on the AAA data we just downloaded here, we're going to look at these data now because they're actually interesting data. I chose those dates for a reason. So,
Laura, before you continue, I think there are some questions in the chat. Maybe.
Oh, sorry.
Yes. I think Mohammed is asking about the.
I think it's basically the difference between like a response row and like you know, the response table from different providers.
Yeah. Yeah. Okay. So let's have a look. So again, oops, if we look at this results, this is providing two providers, right? So if we do 0, 0, that's going to give us the first provider and the first row. So if we do 0, 0, it's providing this one row. If you want to do, so this one is the table number, and then this is the row number. And we can see it's going to do this. So I guess it's a little bit confusing when you only have one search result and you only have one provider. Why do you need to do result of 0, 0? So I guess the question is, the first one is the query response, which is the full table. And then the second one you have there, Mohammed, is the individual row. I don't know if that answered your question quite well. So yeah, so the second one is the row, and then the first one is the provider.
Maybe you could just show what happens if you try and go index too far in the rows. Like, so if
Yeah,
you try and get row 10.
What was I doing? Yeah, it's out of index.
So yeah, so I think that what was happening to you is that you were trying to ask for a row which didn't exist, and you were getting an error. Okay.
Sorry, yeah, if there's questions in the chat, just let me know. Sometimes I can't see them. Okay, are we okay to move on? Yeah, okay. All right, so we've seen how we can download the data, but let's look at how we can kind of, you know, read in this data now. And as I alluded to in the talk, you know, there are two main types of data containers Sunpi currently provides. These are time series and map, and you'll see in Jane's tutorial, there also is radio spectra that's built upon things in Sunpi, but for today, we're only going to look at time series and map. So to begin, let's look at time series. So as it describes, it is a way to kind of hold time series. They're light curves, essentially of measurements and times associated with those measurements. Within Sunpi, the current kind of underlying structure of a Sunpi time series is actually a pandas data frame. So if anybody's familiar, I'm sure you've used a pandas data frame before if you've read in CSV files or Excel files or things like that. It's a really kind of powerful framework to deal with time series data. And I think what Sunpi provides over pandas data frame is it provides kind of readers to be able to read these data and load it into a time series object. And it lets you do this irrespective of the type of file that it is. So if it currently supports a FITS file or a netcdf file or a CSV file, it will automatically detect that file and know what the source is and read the metadata. And then it holds this metadata and units associated with that time series within this time series class. So a way we can create a time series is by essentially instantiating it by time series, and then you pass a file. You can also create custom time series by passing times and data, but for today, we're just going to look at how you can pass a file. So this file here is actually something we downloaded above. So you should have this locally if everything worked above. It's a netcdf file which holds the GOES data. So if we run that, we can now see that it's read it in and it knows that it's a Sunpi time series and it's an XRS time series. So it was able to recognize from the file that it's a GOES XRS data file. We can also then quickly inspect the data. So we can do xrs.peak, which will quickly kind of plot the data and show you it. And if we look at this data, this is the 2 wavelength bands you would have seen from Shane's talk. And we can see there's a nice big flare during the day of this event. So we've created time series update. Let's just inspect, what is this container and what kind of things it has associated with it. This is why it's kind of useful, going back to using Astrophy Units, this data now we have a unit associated with it that's going to be carried around if you ever do any manipulation to that data. It also holds all the meta information about it. So, we have the start and the end time of all the data in the file. So we can see it's, 24-hour data. It has all the different metadata that's in the netcdf file. You can also then access the data itself. So you can get at the data frame. So we can see you have the short channel and the long channel of goes. You can print out the columns. You can pull out each individual row, for example, or each individual column. And you can see when you pull out the quantity, it still has its units associated with it. Let's say, for example, you're like, I don't really care about any of the things time series can do. I don't care about units. I don't care about metadata. I just want to have this as a pandas data frame. You can easily do xrs.toData frame. And then you can export this as a CSV file, as whatever type of file you might want to do with it. And then, of course, you can do whatever things that pandas offers you. And this is the idea, again, of kind of allowing you to read in the data and then go and do whatever you want to do with all the different Python packages that are available.
Right. Sorry, Laura, can I just bring you back there a
Yeah.
little bit? I was just looking at the, what is line 40 there, where you have xrs equals sunpi.timeseries.timeseries equals, and then you have the file name.
Yeah.
I'm used to seeing a start time and an end time, and then you pull it in. But when you specify that file, that's a file at a given time, right?
Yeah. Yeah.
How does it make a decision on how wide the window is then going to be?
So it literally just reads whatever's in that file and then creates a time series based on the data within that file.
So that file has multiple images in it.
So this is just a goes XRS file of a day of observations. So if we, that's what I mean, when you click .meta, this is the information that's in that file. It has, this is the start time and this is the end time of all the data that's in that file.
Okay, I didn't understand what that file name was. I thought it was referring to the goes SUVI data above.
Oh, sorry. Yeah. So if we look here, I have that file locally.
Where would I get that file name from?
So if you, this is where it's actually downloaded. Yeah, here. So I did a file.fetch in that result, and you can see it downloaded that file into my local path. So if you run that, you should have that file locally.
Oh yeah. Yeah, I ran that. Yeah, okay. I didn't. Yeah, okay.
Sorry, I should be more explicit there.
No, I didn't realize it was the XRS file. It says it in the name, so I should have been aware of that.
No, that's okay. It's a good question because I'm sure other people have it. So yeah, if anybody's not aware, this is just a file name that was downloaded above. You can also give this a list of files, or you can also give it some URLs, and it will also read in the data. But this file should be locally stored if you currently have it online. If you currently did the URLs above. I think, Peter, because you use the pass thing within Sunpi, where they had this light curve object that you gave it a start and an end time, and you used to download the data for you and do all that. Now it's changed as this workflow, which kind of makes a bit more sense. Is like you go and get your data, then you have these readers for your data, and then you manipulate your data.
Sorry, Laura, before I continue, I just wanted to address everyone and ask people to speak up and use their microphones if they have any questions. I think this is meant to be as interactive as possible, so please don't be shy. And I'm sure Laura and Shane be able to answer most of your questions.
Yeah, please do ask away.
And if you're not comfortable speaking, then definitely just put a message in either the Slack channel or the chat window. But yeah, please do ask any sort of question, even if it's not directly related to what we're talking about. If it's
So like a good question might be, how do I know if my file is going to be supported in Sunpi? That's a great question. And if we go to our documentation, it will tell you the current list of available time series, current list of data that's currently supported. If you pass a file that it's not supported, so let's just see what happens if I do this. If I try to read an AIA file into time series, it's going to say, you know, it couldn't find a matching class, right? So it didn't know how to read this into time series. And you will get that error then if you try to pass it a file it doesn't understand. So this is why it's important to kind of maybe have a look at the documentation to understand what files are currently read into Sunpi. If there's one that you don't, you know, I have this file and it doesn't work, raise an issue and let us know. Maybe we can make a reader for it.
Right.
So,
I was going to ask what the procedure is for like new types of data or sources for data.
Yeah, I mean, this is a great way to go to the GitHub page and to raise an issue if you're comfortable with GitHub. If you're not comfortable with GitHub, we have a mailing list. We also have that discourse page, which I'll send around the links at the end. So just again, it's just like, I'd love to have this in Sunpi, or how do I do this? Because it might already be there, or there's definitely scope to build it in there. So absolutely.
Cool.
But all of the main ones that you'd possibly want to use for kind of general solar physics is currently within Sunpi. It'd be things that might be a bit more niche that might not necessarily be in there yet.
Is there a Callisto interface? There must be, right?
Yes.
Yeah, yeah. So Shane will work on that. Is it tomorrow or Wednesday, Shane?
Tomorrow. Tomorrow's radio.
Tomorrow.
Yeah, tomorrow.
Yeah. So Shane's going to talk about, you know, all the different kinds of ways you can use FIDO to look for radio specific data, and then how do you read that into, you know, you don't want a time series object, you don't want a map, you want, you know, something like a dynamic spectra object, and that's what Shane will talk about then tomorrow. But it'll be kind of the same functionality. It will have like .units, it will have .meta, it will have those things associated with it, and that's what we're trying to kind of keep going through at Sunpi, is to have kind of this common format of data containers and things like that. Is that okay? Any other questions?
Yes, please. I have a question.
Yeah.
Hi. So I have a problem in the first cell in the time series section. When retrieving the time series source, it shows an error message, no match error. Couldn't find any time series sources to parse. I just added the directory in which the data file is exists, but for some reason it didn't it couldn't be parsed.
Oh, really? And what does the file look like? This file name?
Yes. Yeah. Exactly. Yeah.
It's really strange. Could you like take a screenshot of your error message and put it in the channel, and then maybe we can help you with it that way? Would that be okay?
Yeah. Sure. Thank you.
It could be something that its download didn't fully download or something.
Sounds like a corrupt download, all right.
Yeah. Maybe if you try to run the few lines above here again, to download the data. Sometimes if the download gets you know, interrupted, the file doesn't download fully, and it can have some errors that way.
Okay.
I'll try and post a few little commands in the Slack channel now, and so Laura can go on.
Okay. Thank you.
Thanks, Mohammed.
I have another question. How similar are these objects and functions and so on to what astronomers might be using? Astropy, I'm sure they have their own libraries to deal with different types of observations, but is the general style the same in Sunpi?
Yeah, that's an excellent question, and it's something that actually is going to change within time series soon. But if we, at the moment, as I said, time series is built on pandas data frames. We're trying to move it to the underlying client will actually be an Astropy table or an Astropy time series. So from a user's perspective, it shouldn't change anything, but underneath the hood, it will be more in line with Astropy. For example, using Astropy time instead of datetime objects here. But in essence, it acts quite similar to the way things are done within Astropy. Like, for example, this 2 data frame in Astropy time series, they have the exact same functionality. They have the exact same .meta, things like that. So the idea is to try to get more in line with those efforts to make sure that you can do cross-disciplinary work quite easily.
And are those better than data frames? Because I mean, data frames are so widely used in general.
Yeah. So it's not. I mean, it just goes back to the fact that this was the debate about whether using data frames or Astropy tables or time series. The reason for going to Astropy tables or time series is that you're then in line with kind of how things are done in Astropy and things like that. But then you can easily transfer it back out to a pandas data frame. So you can still do this and convert it to a pandas data frame.
Yeah, as long as there's an interface.
Yeah.
One of the specific little annoyances or problems is that normal Python date times don't understand leap seconds. Astropy tables and time series do. And because pandas is built on top of normal date times, it can't handle leap seconds. So you have to decide what you want to do when you want to try and go back and forth. So that's just one of the little things where, you know, it's fine. You can still make your export from a time series into a pandas data frame, but you have to basically just drop those leap second time values if you have them.
Yeah, and actually building on that, Jane, like something we talked about recently is that if we have an Astropy table or time series underneath the hood, you can then take into account things like light travel time. So going back to the idea that you have some observation very close to the sun, and then you want to see what that time series looks like at Earth, then you can easily do that if you have Astropy under the hood rather than pandas. That's another main motivation moving forward. But the idea is then again to keep it as user friendly and consistent so that you can go back to pandas if you want to and do all your nice things. Cool. Okay, so I think we looked at pandas data frames, and there's several methods and stuff to manipulate your data. So let's say, for example, we only want to look at, we want to truncate our time series to just between these two times as a flare. We can do that truncate. We can then peek at it and have a look, and we can see, okay, I'm happy with those two times. Then you can create a new time series object, which then is just a truncated version of your old time series object. And then if we print out the metadata, we can see now the metadata has been updated also. So we can see that the time range now goes from 0600 to 0900, whereas before it was the whole time range. And if you want to do other things to manipulate the data, for example, you can change values. For example, we're going to change one of the values to 100. And if we plot it, we can see we've changed that. So that was just a quick introduction to time series, but it's really all the main things that it does. And then you can do whatever you want with a time series based on what kind of pandas can do or their time series functionality. If anybody doesn't have any questions, we'll move on to map, and then when we're kind of finished with this, I'm going to give you kind of some time to play around with it yourself. And I'm sure we'll have a lot more questions then. So map is the second type of data container we're going to talk about, and this is the one that maybe is probably the most useful, I would say, in Sunpi and probably most widely used. It's a data container that allows you to hold, two-dimensional data at the moment with associated coordinate system, and allows you to kind of do lots of different manipulation for any types of data within the heliosphere that has an associated coordinate system, usually defined within the WCS, or the World Coordinate System framework. So again, similar to time series, you just pass it a file, and if it recognizes that file, it'll then be able to create that map. If you give it a file that has competent fits headers that make sense, it should be able to read it even if it doesn't have an underlying client written for it. So what I mean by that, so for example, EUI, we didn't write any client. EUI is a new instrument on Solar Orbiter. Nobody wrote an instrument-specific client about that, but its fits headers kind of follow the standard format, so it could be read in straight away with Sunpi and read in as a map. So in this way, it's a little bit more powerful at the moment than time series, is that it can read in most fits files and create them into a map object. So again, this is an AIA fits file that we downloaded up above. It should be in your local path. If you don't have this file yet, you can go back up and have a look at how you can get it. Similar to time series, except it's a map, it's sunpi.map.map, and you pass it a file. You can similarly pass it a data array and the header information, but for the moment, we're just going to pass it a file. And it has this nice thing, if we just want to print the map, it has this nice overview quick look functionality to plot it if it works. Come on. Yeah, so it'll tell you, print out all the different information about this map, which is really interesting, right? A nice way to kind of get a snapshot view. Has the meta information, such as the detector, the wavelength, the observing time, the exposure time, the dimension of the data. Interesting, it looks at the distribution of pixel values. You can also click on this, and it will also show you the cumulative number of pixels, which is nice. This is what the data looks like in world, like within its coordinate frame. So again, we're looking at helioprojective. We've talked a lot about that. If you click on it, it also shows you what it looks like in pixel space, right? So this is the underlying array. Obviously, if you look at the array values for 4K by 4K, then you can click on it again. It will show you it within its associated coordinate frame, which is nice. Now, similar to map, and this is kind of where we're going to get in this idea of having kind of common interfaces.
All right, so can I interrupt you for a second?
Yeah, sure.
This is a really cool functionality there. Is there any other interfaces other than Jupyter that's available in, or is this just a Jupyter specific display of the metadata and data?
I think it creates a HTML, if I'm not mistaken. Yeah.
I think you can do the same thing from IPython, and it will open a browser and show you this.
Oh, didn't know that. Yeah,
I'd have to go and look up the exact command for it to do that, but you should be able to do that as well.
Yeah, because all that's doing here is creating a little HTML. So yeah, that's it's really handy for inspecting your data.
Yeah, and by now we all work in Jupyter Lab all the time, right? So
yeah. But yeah, there should be a way you can do it with IPython. Maybe we have to look it up, but I think the chain set is correct. But yeah, nice way to inspect your data. And I think this is a really nice way to think about, and we'll talk about this in a minute, the difference between world coordinates and pixel coordinates. And this is going to become really important when we're plotting maps and plotting with WCS axes. Just something to be aware of. Okay, so similar to time series, it has a lot of different attributes associated with the map object. So it has a unit, it has a meta data, so we can see it has all the meta information. It also has other things that are important. So it has an observer coordinate. So this goes back to the idea of why you need an observer coordinate, because it's in helioprojective frame. So if we print it, this is read in from the FITS header. The coordinate is actually given in heliographic Stonyhurst, and this is the coordinate of SDO AIA. So this is the coordinate in space of the spacecraft. It also tells you what the coordinate frame is. So it's a helioprojective frame. It tells you like the observing time, and it also has the observer associated within the frame, right? So again, these are two things to keep in mind. And then other kind of meta information has the wavelength, it has the radius of the sun up in the observation, which is around 945 arc seconds. And then we can plot the data. So the map objects have this plot function, which is essentially just underneath IMSHO or p-color mesh, but it plots it within this WCS axis, which I'll talk about some more down the line. So the World Coordinate System axis. So it's coordinate aware axis. So it knows, this is in arc seconds and things like that. So we can look at the data. It looks nice. We can see this observation is at the same time as the GOES observation. So we're actually observing, this is the flare that we're looking at. This is the corner down here. So again, that's just a quick way to have a little look at the data. And something just to note, this is just passed. You can clip you're just clipping the data within, this percentage interval of the data range. If you didn't do that, of course, it just might look a little bit darker. But you can clip the interval, whatever you want here, which is kind of a nice way to play around with it. Okay, so.
Sorry to interrupt you, but I have a question. I see that the color bar is log spaced.
Yeah.
How would you go about converting it into a linear?
Excellent question. Right. So when we read in AIA map, right, it's aware that it's an AIA map. Oh, no. Yep. Okay. Video of this. So it kind of pulled in plot settings around that AIA map. So these plot settings are in AIA map.plot settings. You can see it's defined a normalization, and this normalization is defined based on the instrument specific ones that were given by the instrument team. For example, you don't want that. You can just change the norm value in here. Let's see, normalize. Oh, colors don't normalize. I think I've imported colors above. Yeah. But you can see, you can't see anything, right? Because it's a lot, but you can also do log norm. So this is the same as plt.imshow. So any keyword arguments to plt.imshow, you can pass in here. So you could do, you know, v min is equal to 100, et cetera, et cetera. So you can play around with it that way. And that colors function is matplotlib.colors, just in case you didn't know, which we imported above. You can also look at the data just by, and it doesn't have any color map associated with it. And this kind of leads on nicely to looking at how do you inspect and manipulate the data. So the data, similar to time series, is just .data. It will return to you a NumPy array, the 2D array of the image. And then you can deal with it like the way you deal with any other NumPy array. You can do data.shape, you can index the data, you can print out, you know, the max and the mean standard deviation of the data. And something to keep in mind is that, you know, this does not necessarily need to be a NumPy array. You can create this into a Dask array if you're interested in doing very large data analysis. But at the moment, in default, it's a NumPy array. And I think I'll skip that part for a minute. This is a way how you deal with going from a world coordinate to a pixel coordinate, but I think we'll come back to that in a second. So we touched on, this is the last thing we'll do before we go to the exercise, is plotting a map, right? So we looked at, you can do AIMap.plot and it will plot your map with all your coordinate information, or you can do plt.imshow and plot the data. But what's really powerful about, you know, using AIMap.plot is that it uses this Astropy visualization WCS axes. So WCS axes means like world coordinate system axes. So it's a coordinate aware axis frame. It's a really good way to represent world coordinates. So this is something that took me a very long time to figure out, especially throughout my PhD. Still sometimes get a bit confused about it. When we're talking about world coordinates, we're talking about coordinates within that coordinate frame, right? So I'm going to go back and it's in arc seconds. So if I go back to, or maybe let's go down here to your map, world coordinates would be, this point here would be 0 around minus 900 arc seconds. So that's what we call world coordinates. It's in arc seconds or in degrees or in some type of coordinate frame. Pixel coordinates is the index or the coordinate within the data array. So the way we were able to index our array up here, they're the pixel coordinates. And this is just something to keep in mind when we're plotting data with Sunpi, because with WCS axes, it defaults to plot in pixel coordinates, but the power of it is that you're able to pass it world coordinates and plot in world coordinates as well. And you can use this by using this transform function, which will then, you have your map and we'll see below, you can pass a world coordinate and pass this and it will know where to plot it on your map. And something to keep in note is that when you do pass coordinates, it has to be in degrees rather than arc seconds, and that will become clear in a second. So just to highlight this, if we look at our data array again, we can do .imshow, and if we want to plot a point on this map, say 500, 500, it's going to plot it here, right? 500, 500 in pixel space. But if we want to plot with WCS axes, what we do is we create a figure, we create a map, we create a submap, and we give it a projection. So we're saying we want this in the coordinate frame of AIA map. We can plot the map. We're going to do that clipped interval again. We can draw the limb. We can draw the grid. Now this is where the power lies. You can plot in pixel coordinates. So similar to up here, you can do 500, 500, and we're going to mark it blue, and we can see it's plotting in the same place. But say, oh, you know what? I have my coordinates in arc seconds, and I want to plot in arc seconds. How do I do that? What you do is you have to pass it in degrees. So 500 arc seconds, this goes back to your units. You can easily convert it to degrees. And the key thing is in here, you pass this transform keyword, and it knows that that's not 500 pixels units, it's 500 world units. And then it will plot it correctly in your world units. So this is something I think that takes a little bit of time to get used to when dealing with WCS axes.
The default aura is just pixels. You don't need to specify.
Yeah.
And then if you want specifically, you need to give it an axis or a world coordinate transform.
Exactly. Yeah. Because you would think, like, I know you think you should just be able to go like this, right? And it should plot, but that
would have been my first thing I'd do.
Yeah, exactly. And this is complicated until you kind of can just get your head around this idea between world coordinates and pixel coordinates, and then it can make a little bit more sense. Because sometimes it's useful to plot in pixel coordinates, sometimes it's useful to plot in world coordinates. But
sorry, I have another question then.
Yeah.
You have given it, what did you give it? World. Now, within the world coordinate system, is there many of them that one could choose from? Like the one that you have there is heliocentric. But remember you showed earlier on, there's a few different ones.
Yeah, exactly. So when you put in this transform world here, what it does, it goes back and sees what projection you're in, and it plots
Okay.
within that projection. But you can pass other frames, and it will plot them in those frames. You could pass here, you know, heliocentric, whatever, and it will plot it somewhere mad, you know.
Like you could potentially plot Carrington longitude on the map somewhere.
Exactly, yeah.
Yeah.
And this actually leads on nicely to the next point, right? So you can also pass in sky coordinate objects to plot on this, right?
Okay.
So let's define two coordinates, one in the coordinate frame and helio projected with the map, one in heliographic Stonyhurst, right? So these are two different coordinate systems. And then we can use this plot chord where you pass it a sky coord object. And what's powerful here is that you don't even need to transform it to AIA map coordinate frame. It'll understand that it wants to go into this AIA map. And if we run this, we can see it's going to plot. So it's going to plot these 2 points. So coordinate 1 is this point down here. And then here we've defined the coordinate 2 in heliographic Stonyhurst, 20 degrees by 30 degrees. And we can see that that kind of makes around sense. We go like 20, yeah. Is that okay?
Yeah.
But in essence, yeah, you're right. You can define whatever points you want in whatever frame you want, and you should just be able to plot it with plot chord.
Okay.
Question. What about projections? Like, could we project this in another way?
Yes, you can. So if we had time, I thought maybe later on we could have a little look at that. So, I mean, you could project this image into
like
Carrington
or whatever.
Say again?
Like the IBEX projection, you know, the crazy Malwide projection and all those different types.
Yeah, once you can define that frame within WCS axes, you can do it to whatever you want. So you just have to create, it uses reproject, which is an Astrophy package, and you can then reproject that image to whatever coordinate frame you want. Like one of the easiest things you can do is you can take this map and see what this map would look like at Mars, and it will be able to transform it to what that view and things like that. So there's I'll link some examples as well in the example gallery about how you can do that. But it should be when I say it's straightforward, once you kind of have a good idea of how this whole framework works, it's very straightforward. But doable once everything's defined in the correct way. Is that okay? And I guess as well as doing points, you can also do lines and different things. Let's just show another example where you can define a great arc. And if this is just defining a great arc between 2 points. If we look, this is just a list of Astrophy coordinates, so a load of different coordinates. And again, we can just pass those coordinates to plot chord and plot it on the map, and it will plot a nice line, which is like this. So it's just a very nice way if you have any coordinates, you can put them into a sky coord object, you can plot it nicely on a map. And the very last thing we'll do before the exercise is to look at how you can create a submap, because this is another thing you'll probably want to do with your map. So essentially, how do you crop a map into a smaller region? And you can do this based on the map.submap function. So you have your AIA map, you go .submap, and you pass it a top right and a bottom left coordinate, and it will crop it. So you can do it two ways. You can pass it a bottom left and top right coordinate, or you can pass it a bottom left and a width and a height. So again, going back to this idea, you have, if it's a physical input, it has to be an Astrophy quantity, and here it's an Astrophy coordinate. We're going to define 2 coordinates. So if we go back to this, say we only want this active region. The bottom left coordinate, say we want around 500 arc seconds and minus 700 arc seconds, which is around here. Our top right, let's say we want out here and around 10 arc seconds. So over this region, we define these 2 coordinates. And it's as straightforward as AIA map.submap. You give it a bottom left and a top right. And now you have a new map, which is contained within submap, which is within this region. Similarly, if you want to create a submap, you can pass it the bottom left coordinate, and you can also give it a width and a height. Again, these have to be in Astrophy units. in similar ways like this. Then we can plot these together, where we can draw a quadrangle or a rectangle, I guess, on the map and kind of show how you can cut out these different regions. And then of course you can go back and play around with different widths and heights you want your submap to be within. And then similarly, say for example, you then want to save your file. Oops. You can just do map.save and then save it out as a FITS file. And then you can read it back in. So we kind of ran through that, but they're kind of the main things you have. And then again, you can inspect these values.
Can we save a PNG?
Yeah, of course. So if you want to, oops, you can just like map.lib if you're blt.save, fig, my fig,
Okay.
PNG. And that will save that into your local file.
Yeah. But not through the map, but just PL.
Yeah, you can save it as, I mean, just at the moment, it only has a writer to a FITS file just because it understands how to get a header information out. But you could, of course, save the data array to something. You could save it to lots of different things. It just doesn't have a .save function onto it. I think you can save it to an ASDF file, an ASDF file. But yeah.
There's a question there in the chat, Laura. Is it possible to crop latitude, longitude on the solar surface?
Latitude and longitude on the solar surface.
So instead of using the arc seconds of the helioprojective,
use degree.
Oh, yeah.
Yeah, you can. Yeah.
Yeah, you just pass in you just change your different coordinate here. So say you could give in like, you wanted to go back and you only wanted, say, between like 30, minus 30 and 30, you could draw a little rectangle here and do it that way. And this is maybe where I will, whoever asked that question, let's try do this in the exercise. I won't do it for you here. So we've kind of rushed through things, but the idea is that you have this notebook and you can go back and reference this. And of course, we're going to be here for the next little while, so ask questions. So this whole notebook was a lot to take in. We looked at how you can search for data, how you can download data, how you can read in that data, how you can manipulate that data, and how you can plot that data. Now, it was an awful lot all at once, but everything that you've done so far, you should have to be able to do this exercise. So what we want you to do is, I guess, to look at a flare that occurred in September 2017. So it was one of the largest X-class flares the past solar cycle. It occurred at approximately 1530 UT, so we have a start time, and it ended at around 2000 UT. So we want you to do some analysis on this flare. So very similar to everything we've done, except it's a separate flare. So these are the kind of main steps that we'd like you to have a look at. So the first one is to find the XRS data. What's going to be new is you want to look at the GOES 15 data. So that's something that's going to be slightly new. And then you have all the functionality you need to plot the time series and truncate it over the flare. Then go and have a look at the AIA data, but don't just look for the 171 angstrom, also look at the 131 angstrom or any other wavelength of your choice. But say, for example, this is a large time range and you don't want to download lots of different data. So maybe just do it 15-minute intervals. So use the A.sample. You want to have to read in these maps and have a little look at them. Can you see where the flare is? Try to make a submap of that flare. And then once you kind of have that and you've played around with this, what I want you to do is then, if you have time and you're finished, go to the Sunpi example gallery. And this has lots of other really cool examples of different things you can do with maps once you have your map read in. So for example, you can, resample your data. I don't know why you might want to do that for this case, but there's lots of different things you can do. So if that's okay, that's kind of something to start with, but of course we're going to be here, and if anybody has any questions or help getting set up, that's I think what we'll do for the next little while.
I have a question right away.
Yeah.
Is the AA map is specific to AA observation? So is there a way to automatically select the images with automatic exposure compensation, for example, or without, so you can study them properly, right? You know that it has this weird thing with the imaging.
That's a really good point. So the way,
or you do it in the usual way by selecting from the metadata, or does it have something already implemented inside?
So the way it is, realistically, what you probably want to do is search for data that has search for the files that have kind of exposure time of 2 seconds or a normalized exposure time.
Yeah.
Or you could read in all your maps and you could then look at the exposure time. Actually, this is an underexposed image, right? So you might not want to use this image. So you could read in all your maps and get rid of the ones that have an exposure time less than 2 seconds.
Yeah.
At the way, like Sunpi won't like kick away any files. It'll just, it's just a container. We'll just hold them and hold that information for you. You can, of course, normalize your data. So you can manipulate your data to, if you wanted to do data exposure time value, you can like normalize your data that way, and then remake that. Like you could have a normalized map.
Yeah, I was just wondering whether it has something built in, because it's a it's its own type of object, the AIA map.
Yeah, I guess the only thing really that's specific to AIA, like to the specific maps that say AIA map or SUVI map, is basically just the scaling for the plotting. And then when it reads the FITS headers, it fixes problems that are known within the FITS headers. And that's basically the only reason why there is individual, like it should all just be read into map if everyone's FITS files are correct, I guess. Yeah. I don't know, Shane, do you have any other points or questions or?
No, I think that was great. I suppose as well, just on the looking for data, so Fido, Sunpi doesn't host any data, and so we can only search for stuff that the providers, so the VSO. So if the VSO provided a way to search for exposure time, then you could do it. But we don't really provide any extra stuff on top of what the data providers give us. So you kind of have to do that sort of more advanced filtering after you've downloaded the data. Or
that's a shame, because that's like half the data is unusable usually.
Yeah, I think, for example, we actually have a DRMS client which goes to JSOC, and I think using that you probably could do what you're saying.
Okay.
You can do much more advanced queries.
So I think you can actually get at it by, right, so this is looking at the client again, and this is the table that returns, and it has an info section, right? And that info section has information about the exposure time. So you can filter the table if you only wanted the exposure times of 2 seconds, for example. This query only had 2 second exposure, but you could then trim down your table and then only download those data, if that makes sense.
Cool.
There's also, another thing to note is that you probably want to prep some of this data, do the AIA prep, and that's where AIA pipe comes in. It just takes a Sunpi map and spits back out a Sunpi map. But that's something we can talk about later on.
Well, no, there's the register function now, right, for AIA, which does prepping.
In AIA pipe.
I don't know.
Yeah, so it basically registers it and updates the pointing is what it does in AIA Pi to prep it, as far as I'm aware.
Right.
But guys, I think for students that are here, this is a really good time. Maybe we'll give it half an hour, maybe, for people to have a go. But please ask questions, or if you're really, really stuck, please let us know.
Yeah, I guess we'll all be hanging around here.
Yeah.
If people want to ask questions.
Yeah.
On that note, I have a question. So I had to drop out and come back, and I'm seeing this error. What part am I on? I am downloading. Wait, can you see my screen now?
Yeah.
So Fido search for XRS data.
Mm-hmm.
Okay, so the results came in. Everything looked fine. I see a table. Fetch the data, and then I tried to just do this simple line here, and it gave me undefined objects must be spliced with integers, or unified response objects, sorry. And then it's within this command, it's just this. Have you seen this before?
If you just print result one, or what does it say?
Yeah, it comes out as those tables as I just showed above there.
I think it just wants you to use only indices.
Yeah.
Oh wait, come here. Are you?
No, this could be me messing up because I had to go out and come back. I just clicked all the way through your stuff and wasn't checking too much, to be honest.
And if you do result of 0, or do type of it, does it? Maybe it looks.
You want result 0?
Yeah.
There we go. Type. Unified response. Maybe am I doing something totally wrong? And also what may be different is I'm just running this in my local machine outside of your environment that you set up, so it may be a different.
Shane, or I keep calling Shane. Sorry, this is an update to 3.0 that now it actually. So in mine that says unified response table, right? Because now they return.
Okay, so I need to update my Sunpi.
Yeah, and this was an update to. Because before you couldn't really search the table, it was really awkward to do. So now we have it that are table. But yeah, that's a.
I also think this is a really good demonstration of why we say that you should have an isolated environment, because you could be working on a paper, and the paper needs a specific version of Sunpi and a specific version of some other library and a specific version of something, and then you don't want to update them because then it'll break your paper workflow. So the idea is that for each kind of section of work, you should have an isolated environment where you install stuff once and then you don't basically update it or touch it. So you don't run into these kind of issues.
Yeah, but what if you're working on a paper and then you decide, then a new cool feature comes out and then you wanna include that in your paper?
Okay, well then you should obviously update your software, but then you've got to redo all the analysis to make sure it hasn't changed.
Yeah,
I mean that's the proper way to do it, but not a lot of people do that. But that really is the answer.
And is there a way to package everything together, like I don't know. I mean the
whole thing,
the library versions of everything that you use for a particular piece of work together with the work itself. Like to create a DOI sort of.
Yeah. I mean, people have done that. There's kind of different levels. I mean, the easiest level is to have a requirements.txt. I mean, and that's basically the simplest level. But then, as we're doing here, if you have a conda environment.yaml, you can kind of specify more things. So you can specify the Python version as well as the dependencies and things like that. So there's different ways of doing that. I don't think we've come up with a defined way, but yeah, you definitely can.
But also to bunch it together with the paper itself, or the LaTeX or something, or maybe write the entire paper in Markdown. Yeah,
JOSS, so the open source journal. What does that stand for, Laura? The Journal of Open Source Software.
Yeah.
So JOSS, the papers are basically written in Markdown, and it's all in GitHub. And it generates the PDFs and stuff. It's really, really cool. But that's
amazing. It's such dedication to reproducibility that needs to come into science, to be honest.
Yeah, for sure.
But like one thing to do is like you might make a GitHub repository, like the way we kind of did here with your environment file, and say this repository is linked to my paper, and then you could put a DOI with that repository. So you could also have your GitHub repository reference as well as your paper, and link them together. I think AppJ are now starting to do that, where you can link software to your, and you can get a separate DOI for it. I think it's a good incentive then for people to make their code available, right? If you can get cited for it.
Sure.
What version did you say is the latest and greatest?
3.0.1, is it?
Yeah.
3.0.1, yeah, that's what I was doing now. Okay, yeah, that was my bad practice of not setting up an environment. I need to get used to that.
Yeah, I mean, to be fair, like what I often do is I have a general environment that isn't specific to anything, and I just install things like crazy into that because it's not specific to a certain bit of analysis, and that way you don't have to worry about like breaking something. But that's just kind of my little thing. I gotta jump off for a couple of minutes. I'll be back on in a few, okay?
Sure. So Laura, I'm not sure if you've seen in the Slack channel on the hands-on solar session, Mohammed is still having a problem reading in that file, even though Pierce passed on his one as well, which I assume works for Pierce, but for Mohammed, it's just not reading in. Maybe I'll copy you into the thread here.
Yeah, actually, maybe a good thing to do, Mohammed, is we can try run. Let's see if we can try run the Sunpi data sample. Maybe for 1 sec. I'll just send it. Okay, Mohammed, I just sent can you just try see if those 2 lines of code work for you? Just to see if it works for the sample data.
Yes, I will try this right now. Yeah.
Excellent.
Okay, so I run these 2 lines, and there is no error. It just the progress bar isn't complete for the last 2 files.
Okay.
I sent you a screenshot on Slack.
Yeah. Okay. Is it still hanging? Maybe just give it a second, because I think some of those files are a little bit big. If you go back to that file, you can try. I left another line there to maybe have a try of that original file, where you add in the source and just tell it XRS. Sometimes that can be a bit funny, but I'm not too sure. Mohammed, you used the environment YAML file to set up this conda environment, did you? Or are you using?
No, I was. I had the Sunpi library updated before, so, and all the other packages.
Okay.
was gonna suggest. Ooh, the camera's off. Sorry, I was gonna suggest that maybe in like 15 minutes time we could just have a little introduction around the room. Maybe everyone could just introduce yourselves and say where you're from and what you're doing, and maybe just show us how far you've gotten if you'd like to, or if you're stuck on anything. I think that would be a nice way to kind of finish up the day. Obviously we can chat away in between now and then, but that would be a good.
Yeah, that's a good idea, Shane.
Can I have a question before that?
Of course.
So I tried to start this example that you gave, and I gave it the time and the instrument for Fido to search. And so I wanted to print out the result for both for the 2017, so whatever, September or something. And the first time I said result, it printed it, and now it doesn't want to print it. It was like you wanted goes 15, and it was only 15, 16, and something else. So what's going on? Help.
Oh, wait, so it's not printing the results anymore, even if you type results? Is that what?
Yep. So I reloaded again. Basically, I ran again. The Fido command, and then I ran the search command.
Would you mind maybe sharing your screen so we can see the error message, and maybe we can help out?
Oh, there is no error. There is no error. There is a warning, a future warning that something will be depreciated or something.
That's fine.
Result, wait a second. Maybe that's it's my fault. Yeah, sorry. I just put it in the wrong box.
No worries, no worries. It's easy to do with Jupyter.
Very easy solutions.
Yeah. The problem with Jupyter. Okay, that's fine.
Yeah. I'll back in 1 second.
No worries, no worries. Yeah, Jupyter is great, but because the order of execution is like not defined, yeah, you can all have problems with things aren't defined or.
Yeah, for some reason it just added a box that's not executable. So that's fine. Okay, thanks.
No worries, no worries.
I am now installing the packages from the environment file, and I will check. I will try again to see. Maybe I have something wrong in the packages.
Okay.
Right. Yeah, it could be something to do with the packages.
Yeah.
It's exactly what I'm doing actually for my errors is reinstall the latest version.
Yeah, isn't that what we do all the time?
So Shane, is this Conda just didn't work for me straight off out of the box, so I need to go back and do it. Is there any other environments that you can use other than Conda? Is that the main one, or?
No. So I just gotta put this up because I wanted to show Common. So this is if you do let me just get rid of this. So if you do parse time ? It'll open up the help for parse time, and this is a Sunpi thing, but this just gives you all of the formats it can parse in terms of text input, but then, as Laura said, like time series, which is from Astrophy, which is what's used under the hood, supports a whole bunch of things. Does this work? I don't know if I've imported it or not. Yeah, so it supports a whole bunch of different parameters: JD, MJD, decimal year, Unix, all these sort of things. So all those sort of time formats are supported, but Sunpi will try and parse these sort of standard-ish ones, if that makes sense.
Yeah. I have a question about maps, actually. Yeah. Does Sunpi support 3-dimensional maps?
So when you say 3-dimensional, like as in PFS extrapolations, which are kind of 3-dimensional coordinates, or
Stuff like that.
A time series. Yes and no. I would say no out of the box, but there's work that's being done, like literally at the moment, to try and support that sort of feature.
Right.
But I mean, the main focus of map is for 2D images. Now, you could have a sequence of maps where the third dimension is time, and that's kind of supported at the moment.
But not space. Right, not the other, because it has very nice features for, you know, selecting different parts of it and, you know, reprojecting coordinates and all that stuff.
There's a big update on the way soon. So there's this package called ND Cube, which Danny Ryan and Stuart, one of the main Sunpi developers, have created, and it does exactly that. It handles n-dimensional cubes of data. So it can handle a space-time cube, which would be like maps through time, but it can also handle things like slit spectrographs, where it's a space-time kind of plot, or a space wavelength time, and more advanced things like Stokes parameters and stuff like that. And the idea is that we'll be able to support some of those nice operations on these other kinds of data. I'm not sure when exactly that's going to land, but it's soon, I guess. Laura, soon. TM.
Yeah, I guess it's like, it's supposed to be for 3.0, but I think it's going to be 4.0 by the time it gets in. And the idea then as well that you'd have things like, if you have a load of like an image, if you're doing imaging spectroscopy, then you could hold it in one container and slice through, not only, as Shane said, like in space, you can slice in time and a wavelength and things like that. I mean, you can also do it now in a weird roundabout way. I mean, you could read in loads of maps and then do sequences, but at the moment, it's not a unified.
Or you could like have your 3-dimensional shock model in time and like do stuff with it.
Yeah, like even though you can't do a map, you can use all the coordinate systems.
Yeah. But also, if that's a use case that you have, you know, make an issue for it on Sunpi, so that like we know that that's a use case that you would like to see. And then maybe it doesn't belong in Sunpi, maybe it belongs in a specific little sub package that does that sort of stuff. But this is the kind of thing that, like, if you have a need or you want to see something, it's really important to like make issues or talk to the community, because otherwise, like, it's hard for us to know what people want or would find useful. Like, we don't do ourselves on a day-to-day basis, you know.
But I think this ND Cube would address a lot of that.
I think so.
Joe has a quick question in the chat there.
It sounds like you're missing the brackets, Joe, but I can't be sure.
Can you read out what
would they be, Shane?
The round brackets after peak, so it should be like, you know, xrs.peak or whatever. Yeah, okay, I'm sure Laura just typed in digit. Yeah. Okay,
let me just try that. Well, how about that? Thanks, Shane.
No worries.
You were just talking about ND Cube there, Shane, and we did have some brief chats before with Danny, and I also know that Bin Chen was talking about this for I-LOFAR, is putting in radio imaging spectroscopy data into ND cubed or having a sample of it. Has anyone actually gotten to that yet? I know I planned to do it for LOFAR, but it was on the long to-do list, you know?
Yeah, I don't think anyone has, at least not to my knowledge.
It should just work. I mean, I know again,
Yeah.
this like thing of it should just work, because I tried it with like the LOFAR, like a LOFAR image cube, and just read into ND cube, right? And then I think the idea is then you can play around with it yourself, but nobody's like built on top of it to fully make it work in map.
Yeah, you could see it working so well though. I mean, it's such a use case for it. No.
Yeah.
And he's keen to make that use case. Maybe MWA guys have done it something similar with like that common, have they?
I'm not aware of anything like this. No. I mean, people do make 3D data cubes, but they just save them as
big blocks. Yeah.
Yeah.
I think the key thing is having the right meta information in the fit headers that allows you to construct a proper n-dimensional cube, because basically the way ND cube works, for the most part, it doesn't have to be, but it is a WCS axes object. So like all of the axes can be WCS coordinates, so time, wave, space, or whatever, but you can incorporate other non-WCS coordinates as well.
Well, you don't need to. I mean, it's all standard stuff. It just has to be implemented, I think. It doesn't seem that difficult.
No, I don't think it would be.
Yeah, but it would take someone who's like interested in having it to get on it.
That's it. Like you kind of need someone who's willing to lead the development. I mean, so the reason Radio Spectra has kind of been updated recently is because I want to use it to do Parker Solar Probe, Solar Orbiter, STIX radio analysis, and I don't want to have to deal with IDL stuff and other annoying things. So I'm starting to put some effort into that. So I definitely think you have to have someone with skin in the game, for want of a better phrase.
Yeah. Well, I think we definitely do here in Sofia, and I know people, you guys in Dublin have an interest, so we can, and I'm sure Pietro and Richard perhaps have an interest to do that. So.
Yeah, I mean, for example, currently Radio Spectra is just a simple array in the background, but my next job is to make it be an ND cube, because some of the spectrograms have Stokes data. For example, Orphée has Stokes, and it would be nice if you could put that into, you know, a cube where one of the dimensions is the Stokes information. Things like that are on the horizon, but not yet done. All right, we're coming up to 15 minutes, so maybe we could do that little quick around the room. Maybe people could introduce themselves and just say how they're getting on. If you're happy, you could show us what you've got so far. You don't have to, but it would be good. I don't know how to start. Unless someone wants to volunteer to start, that would be amazing, because then I wouldn't have to try and pick someone.
I can go ahead. Start.
That'd be great, Cam.
Yeah. Hi. So my name is Kamen Kuzarev. I'm a research associate professor at the Institute of Astronomy at the Bulgarian Academy of Sciences, and yeah, I like the sun, solar activity, and I want to learn everything about Sunpi and LOFAR.
Great.
How did you get on with the notebook, Cameron? Did you get or I guess you're talking lots with us.
The what?
Did you get the exercise?
I got to the first part where I'm able to truncate and plot the GOES X-ray stuff. I've been talking too much.
That's awesome. Thanks.
Maybe I'll go second.
Yeah.
The background, I haven't changed it since the previous telecoms, and So my name is Antoinetta or Tony Antonova, and I'm also from the Institute of Astronomy. And for years, I've been wrongly accused of being a solar physicist because I was working with one. But I'm actually working on stellar physics on active stars, which have some things in common, especially when it comes to the activity. I've been using notebooks for like test data and Kepler data and things like this. And I'm just trying to figure out the Sunpi because it has a bit of differences.
Have you been using a lot of Astropy stuff?
Yeah, but I'm a user, you know. I can basically run a code and try to figure out what I need to do to make it run the way I want to or on the data I want to and things like this. Anyway.
That's great. And how have you been finding the notebooks? Is it easy enough to follow along? You think you're...
Oh yeah. I have no background in any kind of Python coding or anything, and I just basically use tutorials and teach myself. And the notebooks are very, very useful in that sense because you can follow what's happening, and they give you the errors that you can actually follow as well and figure out. And the problem is when you paste something in the wrong field, then there is no error.
Well, I'll go third. So I'm Peter Petkov from the Technical University of Sofia. My background is antennas and microwave engineering and electrodynamics. And the things I saw here today are of great interest because electromagnetics seems to be highly involved in the solar process. So we'll follow the course with great interest. Thank you for the nice presentation, guys.
Great, thanks.
Where I can go next. Okay, so hello everyone. My name is Muhammad Nidal. I am a second year PhD student at the Institute of Astronomy, and Dr. Kamen Kozarev is my supervisor. And we also work with Dr. Rositsa and Dr. Oleg Stepanyuk. And my PhD work is mainly about observations, analysis of coronal shock waves, and modeling the associated solar energetic particles, the acceleration and the transport from the sun to 1 AU. And yeah, I have been using notebooks for a couple of years now. And I really think this is a perfect opportunity to learn and get more hands-on training because it's really useful. And I'm also interested in machine learning applications, especially in solar physics. Thank you for these great presentations.
Great, thanks very much.
Who's next on the list? You can go down the list of the chat window, I think, Shane, no?
Oh, can we? Does it keep changing? I don't know. I wasn't really...
I don't know.
Yeah, sure, okay. Pierce is next then, if that's what we're doing. Is he? No.
Sure, I'll talk a little bit about myself as well, why not? Hi everyone, I'm Pierce Murphy. I'm a final year PhD student here in the Dublin Institute for Advanced Studies and at Trinity College Dublin, working with Shane, Owen, Peter, Laura, all those good people who've been talking today. And yeah, my interest is studying the sun with LOFAR, using radio interferometric imaging of the sun with LOFAR, in particular type 3 radio bursts, and what that can tell us about the solar corona and all the little things that are going on in there. And as far as the Jupyter tutorial is going, it's great. I've definitely used Sunpi here and there and everywhere throughout my PhD, but it's nice to see it all laid out and like some of the things that I didn't quite understand explained and all the cool little tips and tricks that you can pick up along the way too. So that's fun, yeah.
Perfect. Thanks, Pierce. yeah, so the list keeps changing for me, so I don't know. Anyone else want to volunteer? Who's left?
Me, maybe?
Sure.
Sorry, hello, I'm Beijing. I think some of you may have known me. I am a newly graduated PhD now. My recent research is on the wave propagation effect of solar radio bursts. I'm currently doing two kind of study. One is using the simulation to study how the wave is propagating and how the propagation effect can really affect the properties of imaging and spectroscopy. And another method is to use observation, majorly LOFAR, to do some observations confirmation to kind of verify the simulation results. In that case, we can eliminate the propagation effect to see what's really happening at the real source. Then we can talk about the emission mechanisms and the energy budget, how the wave is generated, and how much energy we need, and how much is emitted. So that's all. Thank you.
Great, thanks, Peyton. I can't pronounce names here. Does it the other Mohammed from Mohammed Essam or Untitled? I know.
Yes, hello.
Hi.
Hi. Yeah, so my name is Mohammed, and I'm from Egypt as well. I've been working with my friend Mohammed Nidal. Right now, like he's with you there, but I'm in Moscow right now doing my PhD in planetary science. So basically, I'm studying the effect of solar activities on the surface of the moon and Mars. And mainly right now, I'm studying the plasma physics of the planetary surface, mainly on these projects, and working on the other hand on the project ExoMars. They're gonna hopefully will be launched soon, maybe by the end of this year or 2022. Actually, I'm enjoying this this session and all this information. Of course, a lot of information is kind of a bit new for me because I'm a bit far from solar physics, but I'm really enjoying it. I'm learning learning a lot till now. Maybe I've joined you today a bit later, but I'm pretty sure that in the next few days I will learn more and more, and hopefully, of course, after that I will be in touch with you guys to learn more from you, and yeah, hopefully as well to meet you one day. Yeah.
Perfect. Sounds very, very interesting work.
Thank you.
A little bit different.
Thank you.
Are you using radio observations in your for the what you're studying for the moon and Mars?
We are planning to use it, but not yet. Because just I finished my first year of PhD, so right now I'm still studying the basic the basic solar activities like CME, solar wind, and so on. But we are planning to use radio activities, of course. Yeah, maybe in few months, hopefully this year.
Okay, and using LOFAR, yeah.
Yeah. Yes, of course.
Okay. Very interesting. Look forward to seeing it.
Yeah, of course, it's very interesting. Actually, I'm looking forward to to work with it because I feel I was reading about it, and actually it's very interesting. Very interesting topic, and I suppose it's very promising actually in this field.
Great, thank you.
Yeah, thank you.
Perfect. Antonetta, if I haven't butchered how to pronounce that. Or Joe, you can always go either.
Very good of you, Shane. My name is Joe Macaulay. I'm a Senior Experimental Officer in the School of Physics in Trinity College in Dublin. I've been working with LOFAR for a long time, on and off, doing lots of different things, jack of all trades. And my main interest in this is actually the coding and learning a little bit more Python stuff.
Perfect. That's grand. All right. I mean, I think myself and Laura and Peter have already spoken today, so you know who we are. And I don't know, Owen, do you want to?
Yeah, I guess my name's Owen Carley. I'm a research fellow like Shane in the Dublin Institute for Advanced Studies. And I use LOFAR to study when the sun goes bang. I use LOFAR to study CMEs, solar flares, all sorts of radioactivity associated with that, from plasma emission to gyrosynchrotron maybe. And I'll be talking about all those radio emission mechanisms tomorrow. And we'll also be delivering some more Jupyter Notebooks tomorrow to do how to use LOFAR radio data and all sorts of different types of radio data as well. So looking forward to doing that one.
Grand. I don't know.
And I'm currently trying to install Conda, getting there with Jupyter Notebook, loving it so far, and actually learning stuff myself as well. So, yeah, thanks for the intro to the Sunpi tutorial has been really interesting for me as well.
Yeah, and actually to go back to your question earlier, Owen, like Conda is just an easy way to get the right version of Python that you need. Well, usually I say an easy way, but if you have like Python 3.7 or newer, it already has virtual env support built into it. So you don't actually need anything else other than Python, as long as it's 3.7 or newer. And you can actually make virtual environments and do everything just using Python. So it kind of depends on the level of kind of.
Does it have the same good package management?
No, it's basically just you pip install a requirements.txt. So yeah, it's not as powerful because you can't specify the Python version and other stuff like that. But you know, it's a little bit less if you already have Python installed. And then there's also another package called PYN, which is what I actually use, and that allows you to have install multiple different versions of Python on your machine and have virtual environments for like, you know, Python 3.6, Python 3.7, and all sorts of other Python versions. So there are lots of ways of getting it. Just Conda is usually the path of least resistance, except maybe not in your case, Owen.
Sorry, I have a question. You said you're using what package? PYN?
PYN is what I use.
Does it support also 2 point something Python?
Don't do that.
2 point something and 3 point something?
I don't actually know. I would say not, but maybe.
Why do you need Python 2?
Because there is this body software that runs under Python 2.7, and there is not a newer version. And I need
Should be easy to rewrite if it's not big.
Excellent, be my guest.
So yeah, I'm just checking here, and yes, you can use PYN to install an old Python version. But as Cameron said, I mean, not recommended, but you know, if you have to, you can.
Yeah.
I'll post a link into the Slack general channel after this.
Okay, thanks.
No worries. Okay, we're just at 4 o'clock Irish time now, which is when I think we should be finishing up, unless there are any last minute questions or anyone else has anything they'd like to contribute. Okay.
Well, sorry, hopefully
No,
a quick one.
No, go for it.
On the Fido.search, you know, you're saying you can use, you can pipe and OR and all that sort of thing. How far can you go with that? Because I think I have XRS or instrument A and wavelength 171 or wavelength 193, and I think it's all slowing down an awful lot. Is it just that I've done it stupidly, or is there like does it inherently slow everything down because it has to look through more things? Or does any of that make sense?
Yeah, I think. Sorry, Shane, you go.
No, you go. I don't know.
I think it is going to, of course, inherently slow things down, but not, well, like, I don't know whether it'd be slower than calling them each individually. I think to make it tidier, what you can do is you can put one search thing in one bracket, like one parentheses bracket. So like A.instrument AI, A.wavelength 171, and then pipe A.instrument, AIA, A.instrument, A.wavelength 171 or something like that. But I don't think it should inherently slow it down, unless you're also looking for data you don't really care about.
Yeah, I think, in this one anyway, I think I just don't have the sample in the right place, because it's looking through hours of data.
Yeah.
Okay, cool. Yeah, sorry, that was my one quick thing as well.
Yeah.
It basically takes your query and like turns it into this standard format. So no matter what you give it, the query it runs is it converts it before it runs it. So I think you should be okay. You can kind of make really complex queries and it shouldn't.
Yeah.
It shouldn't make a difference. The only caveat I will say is that some of the clients have to go and make actual HTTP requests to websites. And if you put in a really long time range, some of them can be really slow just because it has to make a lot of requests and get the HTML back and parse it. So that part can be slow, but that's only certain clients, not the VSO basically.
Shane, I posted a query in the chat there. The FIDO search, I worked fine when I just specified XRS. When I tried to do an OR with the rest of it, it still only returns results from one provider.
Interesting. I'm just going to copy paste that into my Jupyter Notebook and run it just to see what happens.
No, pretty much this exact command worked for me when we, as Laura was going through the demonstration there. This is pretty much the command cut and paste from
above
her demo. Except I've changed the dates.
It looks okay to me, Laura. I mean,
I'm just going to look at it as well.
It should be GOES, shouldn't it?
No, XRS. So GOES is the satellite and XRS is the instrument, because newer GOES spacecraft also have a SUVI instrument as well. And so it's named after the detector, which is XRS, which was changed not too long ago, actually.
Oh, okay.
The other thing is the search is very, very slow. Is that normal?
Yeah, this is a problem with the XRS client. So NOAA have essentially we have to if you do a large search or a search for any of them, they don't like you scraping their website, so they kind of block it. So we have to do .stop and wait and run again. So if you just look for AIA, it should be a bit quicker. But what actually the Sunpi one is doing for XRS is actually scraping each of the HTTPs S's of each instrument. It just takes a long time. But hopefully this will be updated when they're going to provide the GOES data through the VSO, and then it should be a bit quicker. But yeah, it's kind of painfully slow at the moment, unfortunately.
Okay.
I have a general question that I was thinking about. You know how people have been using the cloud in general, like Amazon cloud and so on and so forth. And there's even services where for example, for Earth observation, there'll be data on the cloud that you can just go and access. Is there, I mean, have people started thinking about this sort of paradigm of just having everything at some data center and then doing stuff with it directly in the cloud through some sort of service, rather than downloading these huge files? I mean, this is for radio astronomy, that's especially important, I think, and very painful to have to download these huge data sets.
I think people have been looking at it. So yeah, you're right. For Earth observation data, both Google and Amazon have these warehouses of Earth observation data that you can just download. I don't think that there's an equivalent for solar data. I don't really know why. I guess it's a funding thing. I mean, someone must be paying somewhere, or
it's a federal problem, but because it's NASA data, pay Amazon to host it, and then it's actual like it all gets really complicated about where it actually is. It can be backed up on Amazon, but it's not allowed to be hosted there, and then they can't give people access to it. It's a bit of a mess at the moment with AIA data, for example. I think.
Well, I mean, it could be NASA servers or something, some way that you could apply for, instead of applying for funding, apply for, you know, access or
yeah, no, you're dead right. This is in the works at the moment. So Pleiades in California, which is one of the NASA HPCs, and there's also one at Goddard ADAPT, which they've now put on like a huge chunk, not all of the AIA data, they've put on like, you know, a year of it. And they're now trying to set up a pipeline of prepping the data, and then they're going to have it available, like essentially compute times for people who can apply for. Still in such early days, and it's going to be really awkward about would outside of US people be allowed to apply for this. You know, maybe you have to be a US institute and things like that. But there is stuff in the pipeline that's just being very slow.
It would be great if people can, you know, spin up containers and run stuff just using data in the cloud.
I mean, you're preaching to the choir here. I've been saying this for ages, because especially a lot of our workloads are like, go and do a lot of stuff and then just give me the results. So you want to spin up a cluster that scales to a huge size, does work for 5 minutes, and then scales back down because you're finished, which is very different from traditional HPC workloads. I think the main thing is the funding model, because it's pay as you go and we don't really have continuous funding. It's a really difficult problem to try and, like, you know, okay, so if I get, you know, 100 grand and I put that into Google Cloud or Amazon Cloud, how do I make sure that I have enough at the end to finish the project, but I spend enough throughout the project so that, you know, you get a good return on investment in terms of science? Yeah, it's difficult, but I think there's a really big argument to be made for the, you know, just not having to worry about servers and infrastructure. You let someone else take care of all of that stuff that you don't worry about.
But it's sort of the same with supercomputing time, right? Isn't it? You apply for time on Pleiades or something like that, and then you get a chunk of time to do your simulations. So this could be something similar. Instead, you could apply for time instead of money.
Yeah. So just to go back to Joe, your question. So I ran your query and I'm seeing the exact same thing. I can only think that maybe the VSO is down.
Yeah, it seems like the AIA instrument is not returning anything. I've just taken out the XRS stuff and run it with only the AIA, and I'm getting nada.
So this happens from time to time.
Same issue here.
And sometimes the VSO goes down or decides not to respond, and this is what happens.
Okay, so take the rest of the afternoon off, yeah?
Yeah. We can go and check their Facebook page, I think, or their Twitter page. There's somewhere where you're supposed to check, but yeah. And so this is one of the problems. Like, this isn't a Sunpi issue. Like, there's nothing we can do if the people who provide the data aren't providing it. Now, ideally, we should probably throw a warning or something to let you know, but
yeah, that would be nice.
Very sorry, but I have to leave. Otherwise, they're gonna lock me up here at this.
No worries.
They're chasing me out. So have a nice evening. For us, it's evening. It's 6 o'clock. After 6 o'clock. So
okay.
I guess I'll see you tomorrow.
See you tomorrow. Okay, no worries.
Bye.
Tomorrow. Bye. Yeah, I'm gonna shoot off as well because I have another call to attend. But
yeah, I think we're at finishing time now, anyways. Again, unless someone had any last minute questions or.
Well, I still have that question about reprojecting two-dimensional data. Is there
Let me link you
somewhere I can read about how to do this?
Yeah. So if I'm just going to put, this is an example gallery. In the example gallery, there's a few examples there of how to like co-align and reproject images. If you looked at the reproject images to different observers, for example, these are kind of nice little self-contained examples. And these examples should run within the environment you've created without a problem. So hopefully they'll have something you're looking for. But if there's something specific, let us know, of course, and we can see what we can do.
Cool. Well, I guess I mean that goes back to my question about the 3D cubes. But if, for example, if you have a surface in 3 dimensions, right? You could try to project it onto a 2-dimensional surface in different ways. And I just wonder, that's sort of like a geographical type of projection.
Yeah.
I wonder if that thing exists at all. That's probably not in Sunpi, but in general in Python.
I think in the package reproject, you should be able to do that. Those examples are based on. So maybe in their documentation, they might have some examples of that. I'm trying to sure. Hopefully that'll help.
I mean, you could definitely do it with the coordinate stack, as Laura said. So if you have your surface, you know, as defined in like a 3D matrix, and each point has a coordinate, you could then definitely extract the coordinates and do projections and things like that. But it's not built into Sunpi, I guess, because it focuses on 2D stuff. However, there's a Google Summer of Code GSOC project at the moment to support some 3D visualization stuff. I think specifically for PFSPy. So that might be a place to look as well. I know they're trying to do some stuff like that. So you can imagine PFSPy is basically like that. It's, you know, 3-dimensional data, and they're adding the ability to kind of zoom and zoom in and zoom out and plot different field lines. So that would be kind of a similar use case. So you definitely look at that for sure.
Cool, we'll do. Yeah, thanks. Cool.
All right, yeah.
Guys.
There isn't anything else. I think we'll call it a day then, and sure, we'll see everyone tomorrow.
And thanks to Shane and Laura for the tutorial. It was really great. Thanks, guys.
Yeah, absolutely. Thank you.
Good job, Laura.
This was all great.
Talk to you soon. Bye-bye.
Yeah, bye.
Bye. See you tomorrow.
Thank you, guys. Bye-bye.